Hello? Yeah. Ah, that's okay. Yeah. 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 Okay, good afternoon, everyone. Can you hear me? The reason why we have a microphone, well, is actually, there are two main reasons. The first one is because we are trying to make, as you know, a live feed of the workshop, so that if anyone around the world would like to join us, can do it. Regarding that aspect, one of the things I would like to kindly ask everyone is if you can keep your connections not down, but please do not connect to YouTube or something that has a high bandwidth, so that we can ensure that the live streaming is smooth. That's what we hope. I'd like to welcome all of you to this 5th International Middle-Sized League RoboCup workshop. And I think most of us know each other, but there is also some new faces. So I would like to invite at least one person from each team to present rapidly its own team, what's their experience at middle size, and basically why they are here. Okay. Before moving into that, there is also one question I'd like to raise just right now that has to do with our social program. We don't have a lights festival in Aveiro, unfortunately, which is a pity. But in Portugal, at least we have what we consider to be a very rich cuisine. And so we'd like to give you a special experience tonight in terms of, Robin, I hope you enjoy it, in terms of meal. It will start at 8 o'clock. We'll go into details later on. But my question is there anyone that has any particular requests or cannot eat any kind of food? Yes. No, we are not going to eat pork. Our meal will be based on fish, basically. More than that is codfish, which is it's dry codfish, which is very traditional in Portugal. And we normally say that we have 1,001 ways or different ways of cooking codfish, okay? So there is no problem regarding that. And because in the sense that the idea is to have a relaxed dinner, we'll have 2 different entries, then the main course, then dessert. Also there will be some champagne at the beginning. And we hope you can enjoy that throughout the evening and beginning of the night. And hope that you can bring good memories home about that. And basically, in this case, we are not going to give you a menu to select. We have selected previously. But of course, if someone could not have fish, for instance, I could ask them to prepare something else. If that's not the case, even better, then we'll talk about that later on. Okay, so maybe I'd like to give the word to Cambada. I can present Cambada. Okay, I can present Cambada. As most of you know, of course, Cambada has joined the Middle-Sized League back in 2004 for the first time. Well, joined. It was more like a joke, actually, in that year. Until 2007, we actually couldn't do a lot. So we started only in 2007 in real competition. And we've been there since then. This year, unfortunately, we weren't able to be in China for financial reasons. Okay. Sorry. Fernando Ribeiro, you can go. Someone is missing. It's Fernando Ribeiro Framinho. Sorry. And so Cambada has been in the competition since in real competition since 2007 and been periodically and yearly competing in MSL and also in different leagues, I should say, because we have been in SPL, also at home in simulation, longer than actually in MSL, and in simulation 2D and 3D, regarding to RoboCup, of course, our activity in RoboCup. And currently, I'm no longer the team leader. I was the team leader last year, but since I've been appointed trustee of RoboCup, now Ricardo, who is doing his PhD, is now on the phone. Ricardo is doing his PhD with us, is now back again the team leader of Kambala. Okay? And of course, this is our home. Welcome to our home. This is your home too. Next, maybe.
Working, right?
Yeah.
Yeah. So ASML, I think one of the few companies participating in the MSL.
That microphone is very peculiar. You have to put it in front of your mouth.
Like this is better?
Yeah, better.
Yeah. I hear it. I think we're now participating for 2 years. This year was, I think, our first year participating in the actual league. Last year we participated for the first time in Eindhoven for the MSL workshop. It was really, really fun. Yeah, so we're still starting up. We have a lot to learn, but still, yeah, good. I think it's really good. What can I say more? That's good. So I'm Tim,
Yep.
André Paul, the vision guy, Jan Feitsma, the overall guy, and yeah, the overall guy. And simulation as well, I guess, and visualization, most likely. No. My own role is a good question. So it's a bit of vision, but it's mostly André, world model, and a bit of all.
Unfortunately. I'm the team leader currently of the Tech United team. This is Robin, Koen, and Matthias. We're also going to present our goals for this year, what we want to achieve before the next tournament.
Thank you.
Oh, yeah. I'm Andreas Witsch from the Apenoctum team, and we started in 2000. The team started in 2005, so the first tournament was in 2006. And yeah, originally we have a quite flat hierarchy in our team, so we never really have a designated team leader. So more or less every PhD student was a team leader, but since this year this changed because we have a new postdoc who will be the new team leader of the team.
Exclaim.
Yeah. Okay. Obviously, you should give him some time to learn, and yeah. Another important person is Stefan Opfer, because if you have any questions about the upcoming tournament next year, he is responsible and he's part of the local organizing committee. Yeah. Yeah, anything else? Yeah, and Stefan is one of our, let's say, more important students, and because of his good work in the recent years, we bring him with us here, and yeah, he will present his bachelor thesis later on. Okay,
thank you.
I was gonna talk myself, but he's our team leader, so I think it's better for into the presentation.
Just making a short presentation of each team. So if you want to give 2 words about.
First of all, thank you for receiving us. We are, and sorry we are late. One of the students had an exam this morning. We had to wait. So we are a mini team. We participate for a long time, but in the last 5-6 years we didn't do anything. So we participated in 2011 in Istanbul, but just once. We are catching again. We are. The hardware is more or less stable and finished. So we are starting the software. Actually, we are 7 people at the moment. one from mechanics, and all others are from electronics, but they program. So the names, you can present yourself, I guess, or. So okay, we have the names on the slides on the presentation. So you'll see who's working and who's doing what, and I guess it will be easy. Yes, that's all.
Thanks so much. Apart from the teams which are present here, this one, yes, okay. Apart from the teams that are present here today and are going to make their presentations and hopefully let us have some interesting discussion about them, we have also people that does not normally belong to Team Cambada but belongs to our lab. Yeah, IRIS, that's Intelligent Robotics Intelligent Systems Lab, where we are today. And we also have a very, very important invitee, which has been here since September, right? It's Walter from the Netherlands, and he's also going to present his work. And it has been a pleasure to have him here for this period of time. And maybe we hope one day we can have him back for doing something else. So, without further delay, I think we should start with our schedule. And if I'm not wrong, the first presentation will be presented by Carpenautum from Kassel, right? Will you check? Yes, I think so. That's what's in the schedule, if I'm not wrong. By the way, if there is any team that hasn't present or give us their presentations, I would appreciate if you could do that as soon as possible. Okay. You already have your presentation here, I guess.
Present. Yes. Okay.
Just check it.
Okay. So, good evening to all of you. I will present you my bachelor thesis with a title Modeling and Attacking Strategy based on Dynamic Path Planning. So, the contents, I'll start with the goal of my thesis. After this, I will show you the dynamic path planning, which is the base for the attacking strategy. And afterwards, I'll show the conclusion of my test results. So, at first, the goals. We wanted to implement a dynamic path planner, which can be influenced at any time by our ELISA behaviors. So we used an adaptable heuristic for the A-star algorithm, which is the base of the path planning. And the last goal was an expandable attacking strategy that can be expanded by new plans or behaviors. So the base of our path planning approach is the computational geometry algorithms library, in short CGAL, which is an extensive collection of algorithms from the field of computational algebra. Important is that it supports both a Voronoi and a Delaunay diagram, which are the mathematical base for our path planner. So another feature is that supports dynamic inserting of Voronoi centers in an already created Voronoi diagram, which can be used to influence the path planning. Another important feature is the avoidance of degenerated edges and cells, which could be edges with zero length or areas, cells with zero area, which could interfere with the path planning. But there are some disadvantages in this library. It's partially poor documented. If you try to understand the code they have written, you can look for comments. If you find some, you can be happy. But sometimes they even switch the language in the comments, or there are no comments at all. Therefore, some algorithms, you can use them, but it's hard to understand how they even work. The base for our path planner is a Voronoi diagram, which you can see here. Which it is a division of the two-dimensional space into cells by a given set S of Voronoi centers, which are marked here in red. So each Voronoi cell consists of all points in the 2D space which are closest to a given center. So, and for the path planning, we use the borders between these Voronoi cells, which can be separated into edges and vertices, which have the feature that they are have a maximum distance to the neighboring Voronoi centers, which could be obstacles for path planning. So if you follow these edges, you can easily avoid any obstacle. So the path planning approach itself searches a path on the Voronoi edges with an adjusted A-star algorithm and is divided into several steps to ensure that we can react on different situations. One of this is that we calculate a new destination if the actual destination is blocked by perhaps an opponent who is at the location we want to drive to. And it can be dynamically influenced by ELISA behaviors. So the first step of the path planning includes a verification of the corridor between the actual target, which is here, and our robot who wants to plan a path. So if the robot wants to drive from here to here, he has to check if there's a direct way and if we can skip the path planning. As you can see, then another teammate and the ball is blocking the direct path, so we have to actually use the path planner. In general, this is a screenshot of our visualization. So all obstacles are marked in blue. We have used artificial obstacles to force the path planning on the field and some of the surrounding areas. The black dashed lines are the Voronoi edges. The white dashed line is the path it has calculated, and the red dashed line is the corridor check. So the second step during the path planning is the actual use of the A-star algorithm to find the target. If the A-star finds a path to the target, we can use this and drive to the point. If the A-star algorithm doesn't find a target, we calculate a new target next to the old one, so we can at least drive in the direction. The fourth step is a special situation. It could happen that we are surrounded by obstacles, or because of bad light situations, we could see shadows as obstacles. And if the robot is surrounded by obstacles, situations could happen where we cannot move. To avoid this, we try to at least move a bit into the direction of the farthest away of the surrounding opponents to at least make sure that that we don't see shadows, or that we can at least encounter such situations. Another feature of the path planning is the dynamic adding and removal of obstacles. As you can see here, we can block parts of the field with artificial obstacles to counter or to ensure that we stick to the rules in several situations. In this picture, you can see that the opponent here in black has a free kick, and during the free kick, we aren't allowed to get closer than 3 meters to the ball. So it's easy if we add artificial objects with a 3-meter radius around the ball, that the path planner can't even approach the ball or calculate paths which would run through this 3-meter circle. so we can easily avoid disturbing the opponent during standard situations. The next part was modeling an attacking strategy, which consists of several ALISA behaviors and plans, and I'll show you 3 of them. The first one is used for shielding the ball. It's actually a kind of easy calculation. We have our own robot, the closest enemy to the robot, and our target point. So in the first step, we calculate the vector between our robot and the first obstacle. We turn it by 180 degrees and receive this vector, which will be a part of the alignment vector. The second part will be the vector between the own robot and the target point, and the alignment point is a weighted sum of both of them. So if we dribble to a specific point and always keep aligned to this point, we shield the ball from the enemy, so it can't see it. So the closest enemy can't see it at all. During this movement, we have to always ensure that we rotate the robot around the ball, that we can't lose it. That we can't lose the ball, because we could, if we would turn the ball around the robot, we could easily lose it. So the next behavior is checking if a pass is possible. Therefore, we use the Voronoi diagram. In this situation, the robot in ball possession should play a pass because he is blocked by 3 opponents, and the best pass would be over to this one, because he can easily score a goal because he isn't blocked and is able to shoot at the goal. But we have to use this robot as a pass receiver in order to play a possible pass. So this behavior checks if there's a possible pass point, which are marked here in blue. To calculate the pass points, we use the Voronoi vertices and move them closer to our own robot, so that the neighboring opponents couldn't actually get the ball before we can do. So if this behavior finds one of these blue points, it is successful and the next one is triggered, which is the fast pass. The first half of this behavior is the same, like checking for a pass point, but it evaluates the best pass point, and if it finds the best pass point, it sends a message to the pass receiver, here in blue, with the location where the pass will arrive, here. And after this message is sent, the actual pass is played. So the final part is the summary. I've tested the dynamic insertion and removing of obstacles in the Voronoi diagram. So I used around 10 till 1,000 obstacles during insertion and removal, and in the normal amount, like 10 till 100 obstacles, it affected the runtime of our behaviors only slightly. Our runtime shouldn't exceed 33 milliseconds, and insertion and removal of artificial obstacles takes around 1 millisecond if there are many, like 100. And if there are 10 or 20, it's way lower than 1 millisecond. The path planning is normally a very expensive operation, but if we plan a pass through the whole field, it takes around 1 millisecond for 10 to 25 obstacles on the field, and the runtime gets higher if there are even more. If we would have around 100 obstacles on the field, it takes around 17 milliseconds. So in general, the runtime of our behaviors isn't affected, and we can use the path planning without losing too much time. So I've tested these behaviors I've used on our robots, and during the test they successfully avoided obstacles, and most of the time they shielded the ball almost perfectly from the nearest opponent. So, okay. Which one?
On slide number 5, please. Okay,
Yeah.
so this looks like this is static now, so can you also take into account if the dots are moving? So then you know in advance that
This diagram is created every 33 milliseconds. So we calculate on a static one, but it's changed every 33 milliseconds, so we can react on moving obstacles.
so you don't make a proposal that you think it will go that way, so that okay.
Not so far.
Thank you.
Did you include something like hysteresis that you don't get deadlocks? For example, if the situation changes slightly because of noise on your vision, for example, that you think your opponents are slightly moving, they are not, and you might end up in a deadlock because, yeah.
Yeah, we had something like this, but we want to implement it again. So we would fuse all seen enemies of the team, so we can have more steady opponents.
Okay, but you don't keep the path, for example, and say, well, it's still valid because.
No, it's part of the A star of the hysteresis function from the A star search. So if there were already a path in one iteration before, then it tries to keep that path.
Anyone else? You gave us some numbers regarding the performance of the solution, and what is the overall overhead regarding the total software that is running the robot, because this is only part of the job, right? We have Alisa running also on this, and you have an idea? Are you already on the limits regarding the 33 milliseconds? No, you are.
Alisa takes like, a usual Alisa step takes like 1 millisecond, and this
Okay.
one depends on the amount of obstacles, but this current implementation, we can assume that's again 1 millisecond.
Yeah, around.
Okay. Okay. Another short question that has something to do with what we're expecting to do tomorrow. You introduce a lot of artificial obstacles, right?
Yeah.
And do you have an internal way of determining if this is an artificial obstacle or a real obstacle?
Yeah, in our world model we have a list of all obstacles which are currently on the field, and they are you can was heißt unterscheiden? Distinguish
Between them.
Yeah, on an ID we gave them.
Okay.
So we have negative numbers for artificials, positive for real ones.
Very simple solution, right?
Yeah.
Okay, thank you.
One question regarding the implementation. You mentioned that your objective is always to walk on one of those lines,
Yeah.
drive the robot on one of those lines. It's also, the question is also related to the problem that the dots are moving, and if you have one dot that comes down and the other one that goes up, the line will rotate. In terms of implementation, do you try to drive along the line? Do you drive to the next vertex? Or?
Yeah, normally we calculate the full path, but we only use the first vertex as a goal, so it will change every 33 milliseconds, so we can easily avoid if the the opponent is moving.
Okay. Can we move on then? Thank you so much.
Now, better? Yeah.
Yeah.
Okay. What's the button for full screen? Is this one? Control R? L. Okay. For the second part, I just want to give. Yeah, for the second part, I just want to give a small overview about the things we did last year. So basically, there's nothing spectacular in it, but it's just, yeah, to give you a small update. So first of all, we reworked our actuator control device, which is responsible for the grabbers and for all the tiny sensors, let's say. So everything except the camera and the motion device. And one thing why I want to present that one is because there are currently a lot of IoT devices around, and we tried to use one of these IoT devices to have more comfort and have easier maintenance when developing with our robot and when we make changes. And therefore we use this board is called BeagleBone Blackboard. Maybe some of you know it. And one interesting reason to use it is that it is able to run Ubuntu on it and to have a standard Ethernet connection. So we can use all our stuff that we use on the robots too within a ROS middleware and communicate with Ethernet. And this is, yeah, easy to maintain. And the BeagleBone Blackboard, in comparison to the, let's say, Raspberry Pi, has the advantage that it has more digital I/Os and, yeah, so stuff that we need to plug in as much actuators as possible. Yeah. One question that we cannot answer yet is whether it is robust enough for the RoboCup domain, especially whether, I don't know, electrical issues make it break, or I don't know. This is something that we will see in the next tournament, I guess. Just for completeness, these are the devices that are connected. So it's there's an inertia measurement unit that has a gyro, an accelerometer, then we have a light barrier, tiny motor drivers that power the grabbers, an optical flow sensor that we presented in the workshop last year to detect the rotation of the ball, which is still not in a state that we would like to have it, and one servo motor that selects the shovel for the kicking device. Yeah. Another work that is in progress is one of our students is working on a new kicking device, not on the kicking device itself. It's he's developing a board that charges the capacitor for the electrical kicking device. I guess all of the teams are currently using an electrical kicking device, right? Yeah. And I also guess that most of you use a step-up converter to charge the capacitor. Yeah, probably. And his idea is to use an AC transformer to step up the voltage. So if it works, then it would have the advantage that it can change the capacitor more quickly. We have a galvanic isolation, so between the primary and the secondary side. So if something crashes on the right side, the left side will have lesser effect. So we have more safety, and hopefully it's more energy efficient. At least that's what my student told me, so I'm not too good in these kind of electrical stuffs. One definitely disadvantage will be that it has more weight, and we have no experience on that area. So we are not quite sure how we have to dimension other parts that we need to make this conversion work properly. So this is again something where we will see hopefully next year whether it's a good thing to use or not. But is there any other team that ever tried it or any experiences with it? So it's my question to you. Okay. So maybe next year you will, at the next workshop, we will have some update on this one to see whether it's good or not. We also made something in our localization. I assume that all of you know the particle filter approach, which is basically some kind of template matching where you have have some hypothesis on the field and you match whether the line points that you saw match on the field that you have saved in your config or somewhere else. And another approach, which is also very well known, is this gradient descent approach from the tribots, where you just assume that you already have quite a good position, and then you compute the gradient of this position with respect to the error that you have in the same error landscape as in the particle filter, as for the particle filter. And our idea was that we combine both. So for each particle, we make some gradient steps and optimize them to have a more precise position. So we can use this to have less particles and still have the same precision as we would have with a lot of particles. So the good thing about that is by adjusting the number of particles, we can have a global localization, but still have the precision of the gradient approach. And another advantage of the gradient approach is, of course, that it needs less computational power than the particle filter, because you just have some steps and it's usually sufficient to find your position. What we are currently working on is on how we want to select the number of particles and the number of gradient steps, because usually if you have a good localization, you require only a few gradient steps and less particles. And if you have a bad localization or you're completely lost on the field, then you want to have more particles and less gradient steps. And but our question that we have not yet answered is how we adjust these two parameters against each other. And for that reason, we don't have any numbers yet on whether it is better than either of the original approaches. Yeah. And the last thing we are working on is also, again, a student project where we try to make the obstacle detection with ASUS action cameras with a depth camera, similar to the Kinect. It's a very simple idea. We just detect the ground plane. Then we compress the data in a voxel grid, which is more or less, a voxel is nothing else than a pixel in a 3D space. And during this step, we also just throw some uninteresting points away. And then we can remove the ground plane, and the remaining objects are assumed to be obstacles, so either teammates or opponents or the ball. And this looks like this, but on this slide, okay. On my laptop, it did look better. So on my laptop, you could see that here and here are obstacles in a different color. Yeah. Okay. Bit hard to see. Hmm? The green is the ground plane, and where you only see black spots, there are obstacles in red spots. Yeah. And the blue one? That's the wall. Yeah. Side of the field, the blue one on the left. So we would detect the blue one also as an obstacle in practice, except we would, it's also still in progress, but probably we would throw away obstacles that are bigger than an opponent could be. So yeah, that's it. So I just wanted to give you a small roundup on the recent things that we did. Any questions?
Lots of things going on, right, actually.
Yep. Questions?
Do you have any preliminary results on the charging system based on the transformer?
Not yet. It's not
yet.
It's completely conceptual yet.
Okay.
So we have also problems in finding a good transformer that has a proper relation between primary and secondary side Windungen.
Number of calls.
Yeah, exactly.
Right. So. Okay, and on the other things you are working on, are there any preliminary results that you'd like to?
No,
no, it's still ongoing work, no results yet, right?
No results yet, yeah.
Okay. Are we expected to have some of this stuff working in the next tournament?
Yeah, actually that is the goal. I mean, for the charging system, I'm not quite sure, because this is very experimental, and the next tournament is already, it's only 6 months, 7 months, I don't know. So only a few time, and we also have, I mean, the other thing that we are doing, of course, is since you all know that we ported our stuff from C# to C++, so we have to re-implement all our behaviors, just standard situation and on, and yeah.
Just a couple of few questions about the Kinect, because we've been doing some trials also with it. First, do you distinguish the ball between the obstacles, or it is something already known? Because you said the blue was the ball and the other one are obstacles. Can you distinguish between them?
The blue was the ball, not the ball, but
the goal, okay, the goal. So an obstacle is an obstacle, okay.
Yeah, and I guess we can see whether it's the ball or not based on the
signs. And the other question is, from the experiments we've done, I think up to 4 or 5 meters you didn't get any more information. It's probably the same that you get. Yeah. So around 4 or 5 meters you cannot get some reliable information.
Yeah, this depends strongly on the light conditions. So in Istanbul, for example, this was the last time where we evaluated the data from the Kinect at that time. It worked almost up to the midline of the field. So what's this, 9 meters? So it was on the Kinect was on the goalkeeper, and it's like 9 meters. This worked. But we also had areas in our cafeteria, it works like 1 meter.
Yeah, it depends.
So it's even worse.
I was just thinking, right, can you, because you have the depth, but you as well have the normal image, use the normal image that you can see with color where the ball is, and then map that one on the depth?
That's something actually we've been trying to do. It's filtering color within this web from Don Jose. We filtered the problem we have is that you have several balls that are not good balls coming from noise that is there. So we're filtering it with the 3D. That's the opposite. So we say we might have balls on this position, but these one are too far away, so probably this is the one that we are missing. You can do it, but you have limitations because it's up to 3-4 meters. 5 maybe, that's the maximum you have. And we are still working on that. Actually, the last thing we were discussing about it was to try the new Kinect. I think the distance is the same, but it probably has larger resolution, so we have to try to work on it. And there's also a problem that might come up is there are some interference between Kinect. So if everybody starts using Kinect, if you make robot just in front of the other ones, they will not see anything. But the worst, I think, has light illumination. If you have lots of light, then you just forgot it. I was not in the last that we've been, but I just remember Jose told me, I think it was in Villarreal, that forget about Kinect because you cannot see anything.
You should not underestimate the standard directed camera. So if you just search for balls that are from the, if you are the goalkeeper and you just search for balls on the field, then the directed camera is the best thing.
But the idea was to combine, I think.
Yeah.
I learned about trying to combine, not just choosing one of them.
Okay, any more questions? Yes. Thank you so much. Round of applause for opening up. Okay, the next talk will be from ASML Falcons.
Okay. To the left. If you're looking down here, put it on the left.
Better? Yeah. Nice. So, our team update. I'll first talk about what we currently are doing with RoboCup as well. So not the technical part, but the organizational part. Then we'll talk about a bit about the software we're currently at, in which stages and what we want to do before Leipzig. And then we have a hardware thingy as well, the camera. So, but then Andre will talk about this. So contents, our mission, how to call it, for RoboCup, software updates and the new vision system we're working on. And the mission itself, so our team captain
couldn't come, sadly, to this workshop. He wanted to come, so I'll present this now. So within ASML as a company itself, after China especially, more awareness came to this tournament, and it was really good. And ASML itself wants to demonstrate RoboCup to promote technology to schools and to job venues and fairs. This is what we're going to do. So for this we are going to create a new demo team that will do this especially and write our own software specifically for this demoing itself. Furthermore, we think that the Turtle 5K platform that we bought, we can still push something out of this. So we're going to continue progressing with the Turtle 5K platform, but as well in parallel we're going to create our own hardware platform just to do this and have this ready. Furthermore, let's see what I have to say about this. So we're currently optimizing our current hardware and software. I think Jan will talk about a bit about the software parts, and Andre will show something about the new camera then. Furthermore, we're writing and executing test plans just to have a stable platform. So we did a lot of prototyping last year to have some functionality up and running, and now it's time to stabilize and then build further. So as a company, right, we do this voluntarily in our evenings. Yes, we have a big team, 34 people, but that's including logistics, the people that promote us whatsoever. And I think for software-wise, we have like 10 people. So we can do a lot, but still it's just 5 full-time employees, so to say. So 5 times 40 hours a week that we can spend on this, but that's excluding. So I think 1/3 of this is just what we can do in software. So yes, we're a big team, but yeah, it's not progressing that fast as we would like to have this. The activities we want to participate next year, so Dutch Open, March 2016. We're gonna, I think first half year of next year, have 9 demo events. I don't know which one by heart, but yeah, we're gonna do some. Mini games against DOE in our own venue, I guess, and VL Robot Sports. And of course, the World Cup at Leipzig we want to participate in. So this is now currently on the schedule itself. So for software, the updates, the velocities we try to live by. So we really want to share our code with the other teams. I'm still discussing with the legal guys to have the license ready that we can put it online, but we made a decision to actually put stuff online. So we want to put on the whole code base except then the strategy team play parts. When we're programming, we like to keep it simple, right? So the KISS principle, so that it's easily readable for other people as well. And what we're doing as well is we are now really actively refactoring our code, that we have the core functionality in just plain C++, and the ROS interfacing just as a shell around it, so that people can easily pick it up when they're not using ROS itself. So that's good. Furthermore, what we do is behavioral-driven design and use continuous integration, just to have the outer testers ready, and if people start committing code, that we know when some tests fail, that we can quickly steer on this, so that we have a more stable platform. Last slide about this, I just said it. We want to create scalable software, maintainable and testable by the other things I just said in the last slide. We're actively indeed refactoring, reworking our code for this. Furthermore, we want to document our code with Doxygen. I think everybody is familiar with Doxygen, I hope. Yeah? No? Just come ask later, it's fine. And we're now creating, we're really maintaining our wiki pages, that we can have some backup information about the global structure of the code itself, that you know where to begin. Yeah? Jan, I guess it's your slide.
Hello, you hear me? Okay, good. So more about the software specifics. Colors again, not very nice as I had intended them to be. As with the German team, we are also refactoring and transitioning from prototype phase to a more stable phase. But I wanted to zoom in only on the bottom two parts. So in China, we suffered a lot from robots which did not do as they were told, and that was a bit frustrating. So we decided to rewrite the motor controllers from scratch and to solve the serial problems also that came with it. We call it drunken robots. While doing so, making it maintainable, adding new features like not having to connect to flash it anymore. So that's now in testing phase. Finally, we want to use Gazebo, not only for simulation, but also for visualization capabilities, and I'm looking for feedback of other teams of how they would advise to do so we can make a good decision. So that I said for the visualizer. Gazebo has good visualization capabilities, but of course everybody has already a visualizer, so we only have a limited amount of full-time employees, of hours, as Tim told. So we would like to reuse whatever is available and not reinvent the wheels. So if you have feedback on this, then please come find me.
We use the one of Kambada. You can download it.
Yeah, good. So I would like to investigate it further. But also for the simulation loop closure, how do the other teams, how do you solve this, or don't you make use of simulation at all? It's also so I suppose in small size leak, this is heavy on feedback and simulation. So somehow we want to close the loop and generate the refbox commands to have a complete simulated match. So does any of the teams have this in place already? Also? Okay, I should follow up with you then. I have one more slide on team play, the brains of our robots, before Andre continues on the vision elements, so I will not zoom in on the rest. So for team play, again, moving from a prototype phase to a stable, future-proof situation, and a couple of new people who joined after China and are working to refactor it, and we are inspired by the Kambada approach to layer the role manager roles and behaviors and actions. So this is in progress. And that's basically it for the software update. So now, any questions so far? Zal ik even uitzetten. Waar zit er? Oh, die zit natuurlijk hier.
So hello everybody. I'd like to share some information with you about vision things. Check. I have a number of things I'd like to list on. So first, our Turtle 5K vision we currently have, with some limitations we have, and we made a new list with requirements, what we think we would like to have for a new vision system. And if we can find a standard solution which already solves the problem, it's not, so then we go try to do it ourselves. And for that we have a proof of concept with conclusion and then how we'd like to continue. So the Turtle 5K vision we are using, that's the standard thing which was already on there. On the right you see a picture what you can see, and these squares are like 25 centimeters, so you can see about 4.5 meters. But the last section of it, it's pretty blurry, or you get problems with color because the mirror and the tube, on the end they don't work that very well. So there's one quite big disadvantage. So we're not able to see the whole field, only like 3 to 4 meters. And the other one big thing is we have only a down view, so we look down. I'll show you it in the next picture. And then some less important things, but still things which are on list. It's pretty inefficient use of the pixels of the camera because it's just a wide camera like 69, and we only use a circle of it, so the sides we don't use anything of it. And another thing which is difficult is the calibration. It's a mechanical thing to get everything aligned. It's not very nice designed, and the tangent function to correct the mirror is also not really nice. So we need some features for that. And of course, the same problem most of you guys had with 2D. It's not so easy to determine the correct distance of the balls or obstacles. I have this box. So the down view. So at the left you see the robot over there with the mirror looking up there. The point window. So the camera is looking up to the mirror and sees it over there, and we can look up to only 4 meters, but everybody's now starting to use lobbing, and so we don't see the ball at all. So this doesn't make sense. So we have to find a solution which can look higher. So we would like to have something like this. If you can see to 120 degrees, then most stuff we can get. And then we also can look farther, like more than 10 meters, and then we have a limitation, the amount of pixels we can have, and the vibration of the robot, because if the robot is moving a little bit, then it gets blurry in the end, and then it doesn't work anymore. So then we made a list of requirements, what we would like to have for such a system, and we don't need a full view, like 120 degrees vertical would be more than enough, but we still need a 360 degrees around. We would like to have, currently we have only 30 frames per second, but we would like to increase to like 60. We don't need if we use multiple cameras and we have them correctly aligned, we don't need a high resolution, so we expect 800 × 600 would be enough. But we want a low latency, because if the ball is coming in, you need to act on it, and it takes you like 100 milliseconds. That's a waste. And also the other one, if you have multiple cameras, you would like to synchronize the cameras so you can correctly align all the information. And another, if you have like, you can also buy cameras with these wide angle lenses on it, but they have a lot of distortion on the end, so we think we should be below 80 degrees for the main information we would like. And also we had the assembly size, or the size in the top of the robots by the regulations is limited, so it should also not be too big. And the camera should have a normal communication interface, so it's easy to connect somehow, and we would also like to have it compatible with Linux/OpenCV availability, and it should be affordable, so we can buy things of 100,000 euros, but that doesn't make a lot of sense, of course. So that's a long list. So we first looked at standard solutions. As I said before, most of the cameras that can do 360 degrees are large or expensive, or don't have any streaming video. And most of them, that's the one thing, most have a limited vertical view. So most of them can only do like 60 degrees or something, and then we still miss a lot. Like the top one, that's the Samsung depth camera. Very nice thing, but it's very limited in height. But there are two ones which are very nice. That's the Panone. That's actually a 300 × 360 camera. Maybe you saw it. It's pretty funny. They put like 36 small cameras in there, and they match all together. But unfortunately, so they have only 45 degrees for each. They only require 45 degrees for each camera. So they don't have a lot of optical distortion. Very nice. But unfortunately, the streaming is expected maybe in 2015. So they first focus on making just static photos, and that's not for interest, of course. And then the other one, that's the Sphericam. It's 360, but they have only six cameras. And so then you get a lot of, and I've seen those test movies online there, and you see in the end the edges already, there is some distortion already in there. But it can do 60 FPS, but it's not really cheap, like 2K or something like that. And an important thing of most of these cameras, it's closed design. So if you want to tweak something, you're dependent on the API which is provided by the factory. So then we came with the idea, can we not do it ourselves, something like that? Because we are not require really nice, good colors or something like that. We just need some basic information to extract the parameters we require from the vision, like the line points, for instance, or the ball. So like if the Bayer filter isn't working perfectly, we don't care. And you start off, we do the processing on a standard PC, so we'd like to have a standard interface with just a normal CPU box. And we currently have also a webcam, so we thought, okay, if we take webcams for it, they're cheap, they're available all around the corner. And we found this Genius Widecam F100, and this one has a lens like it's 70 degrees by 120 degrees, or 120 by 70 or something like that. If we turn them around, I hope you can see it, but we have stacked here like 8 in a circle, around, and they're looking a little bit down, and then we can get a view. And so the cameras do 180 progressive at 30 frames per second, and they have the degrees what they said. So if I put 8 in a circle, then I have 360 degrees, and I only need, for the normal view, only need 45 degrees. So that's very nice, and they're only 40 euros. But we don't have any experience yet with, we did not have any experience with the bandwidth. If you stick multiple cameras to the PC, what's happening? Latency, the shutter control, how that's working, and can we really achieve the 30 frames per second? Because it's only in the folder. And does the camera control work for it? So for that we did a proof of concept test. Oh sorry, first the visible area. The picture in the right bottom, that's so one of our guys, Raf, made a 3D model of it. So and we can nicely see how it figures out. We started off with 6 cameras in a circle, but then we had still a lot of blind spots, things we couldn't see. So in the end we ended up with 8. So at the right bottom you see what the camera is seeing, and at the top is the top view, so all the things are closed now. And the left picture, that's the nice one, so only the green part, that's the part we cannot see with this setup. So only above ourselves we can see, and just below ourselves we can see, but that's just our own metal, so that doesn't care. And as you can see the blue ball there, that's the thing we can see, so it should be a really big step forward to what we currently have. So then the proof of concept, I tested first with some stuff I could easily get. So I had two of those cameras ready, and I put some other cameras in parallel to test the bandwidth, and some more streams, so to get to 8 streams to total. On just a standard E7 I run this. And you see the setup at the left, so there are the 2 Genius cameras there and 2 of the Logitech cameras, and they look at the fan, and the fan is turning really slow to see the delay between the cameras. And the idea was, if I have these 8 cameras there and I grab them all at exactly the same moment in software, then I would hope that the capture moment would also be the same. And I do this just to make 8 separate threads, and each thread calls the call function, and at the end they join again, so the threads are synchronized in software pretty close. And then the results. What the successor story was, I was easily able to run grab 5 cameras to the USB port, and I even increased the resolution like 1280, that also works pretty fine. If there's enough light, I also can get at 30 frames per second. The camera control also works with standard USB cameras, that's no problem. But I had 2 failures. One is I could only stick up 1 camera per USB hub, so I would like to have 1 hub and stick everything in there, but somehow there's something going low level wrong. I didn't really investigate that, but the big issue is I had a synchronization error for more than 5 milliseconds, and that's a violation of one of our requirements to get things accurate. And this is the picture I've taken. So it's the same, it's a fan which is turning, so it's a little bit blurry image. So the left 2 images are with the white cam, and the right 2 images are with the Logitech camera. And you can see that the camera is running. I would expect that if the software would align it correctly and the grabbing would be aligned, I think the grabbing actually is aligned correctly, but the camera inside does its own synchronization. And yeah, there is like 20 degrees offset off, so that means it's 14 milliseconds. So I tried around and I Googled around, and it's pretty difficult to get stuff synchronized like that. So I think the idea is that the cameras just have their own 30 Hz running there, and you're not able to tweak with it somehow or get it synchronized, yeah. And it's a webcam thing, so it's a closed design, and we don't know about how it's working. We think it's a dead end. So a sad story, but we learned something from it. So now how we are going to continue? We can still go out and buy really those expensive industrial cameras, like 1K each or something like that. But we first like to investigate in just standard things. And as you know, the current smartphones have pretty nice cameras. And what I mostly see is they are from the brand OmniVision, or from the Optima sensor thing. That's from Micron memories, and OnSemi, that's taken over again. And yeah, they're just simple chips, and they're really cheap, like a few dollars. And for instance, the Raspberry Pi camera, maybe you've heard of it, that has also one of those cameras. You see it on the left there, so that's the Raspberry Pi camera connected to a Raspberry Pi. But also the standard Raspberry Pi camera also does not have the shutter control. They didn't put the wiring on there. But another company called RoboCup, they redesigned the Raspberry Pi camera and put the additional synchronization wires on it. So theoretically, it should be possible to get it synchronized. So and we don't know yet how we want to connect all those cameras, but because in that case we would like to have 8 or maybe 12 of those Raspberry Pi cameras, 8 or 16 of those cameras on one system, and then we get a lot of wiring, and to give every camera Raspberry Pi, that would be a little junky. So probably we're going to hook them up to an FPGA board and use the FPGA as a collector of the information and send it then to the CPU box. And in the end, we also might add multiple of those to make stereoscopy for that. That's the long future thing. Any questions? Yep.
I think that one of the difficulties with cameras like that is that you don't have any information. So if you see a yellow blob, for example, and you think that's a ball,
yep.
And how do you know that it's not outside the field? That's one of the biggest problems with us. So we project balls on the field. When it's in the air, we don't know whether it's in the audience or whether it's really a ball which is in the game. And you don't have any depth information, so you don't know what the size of the ball should be.
Yeah, that's correct. Yeah, that's correct. But there's always, that could be a discussion like it could be in the field or not, but if you start driving or the ball is moving, if you take multiple images, you can make probably a good guess where it's going. But you're right, it's still like Kinect or something, or that would be way better, but then we need a lot of Kinects and we expect we get more latency, and so yeah, it's a difficult thing.
Do you have any idea whether you can, so you want to do the vision processing on the FPGA as well, or do you want to do that on the?
No, we did not yet make a final decision on that, so I think that's just going, I think we start off with the PC box and use the FPGA, start off using the FPGA just as the grabber to get the information in the PC, because we cannot hook up these things directly to the PC, and FPGA has that advantage that you can get the clock synchronization stuff very easily in there, and it's working 100% because it's direct hardware. And then get that information somewhere in the PC and do then the processing. But it could be in the end that we move some pre-processing to the FPGA, or maybe we would even move to a GPU.
Do you have any idea whether you can run it on a computer? Do you have enough processing power to process all those images?
Yeah,
because we have some difficulties with that. But
yeah, we think we can. First of all, the main algorithm doesn't change that much. It's like we burn most of the CPU power in localization. But the problem for the localization is the same. So I have the pre-processing, and after the pre-processing you get a line points, and I get like 100 line points, and they get in the localization. So that algorithm will stay pretty much the same. And
you will have 8 times more pixels to process.
I have a lot more pixels. Yeah, that's correct. So it could be that I need to offload that pre-processing to the FPGA, and that's again pretty simple because that's just the color filtering, and so that's not a rocket science thing, and it's also pretty easy to implement in an FPGA. Or in a GPU, yeah. No, it's not a fight. It's like, I think we do both or whatever.
Questions?
You can also reduce the resolution of the cameras. I mean, and you end up with the same resolution that you had before. It's the standard mirror camera system. But you can adjust it somehow. You have a parameter. You can adjust the computational power. You can just reduce the resolution of each camera.
That's correct, yes, that's correct, yeah. That's the reason I also put in there like 800 times 600. That's pretty low for a camera. That would be pretty sufficient, we expect.
Okay, but then you will still have a lot.
Sorry?
But with 8 cameras, where each camera has 800 by 600, then you would have still a lot of pixels. But you could go down to, I don't know, still enough, I guess.
So that's the reason, one of the reasons that we did already this test. So I have done this test. This is actually, one back. What I did with this proof of concept test is test already with 8. So I have 2 hardware connected, there are 5 hardware connected cameras already in this test. And I have 3 additional streams in there. And I can easily run also the streams already on 1280. So the processing to get it into the pre-processing, that's no big deal. That the CPU, an Intl, so a 4-core CPU can do it easily. So it's just like the information gets stored in the DDR memory, and there are some efficient calculations. Actually, that's not my thing. That's OpenCV. Somewhere below there, they do some very nice tricks, I think, but it just works. So I'm not concerned about that much.
Any further questions? How do you do the, let's say, white balance and brightness adjustment of the camera, currently or in the future?
So, sorry?
Currently, how do you do it? And do you think that you change the way you do it in the future? That two questions.
That's a very good question, actually. The white balance we currently have also an issue because the auto white balance of the camera doesn't work very well. So when we start a match, we just manually figure out how much Kelvin color we have. Like, okay, this is a 5000 Kelvin thingy, and we distribute that information to all the cameras. But now it will be more if you go for this smartphone cameras, we have to do all these things by ourselves. So we have to make some procedure to do some calibration over there. And I'm not sure if we can do it automatically, but I'm also not sure if that's a real hard requirement because when you start the game, in most cases the light conditions will be pretty much the same.
That may not be true in the future, but
yeah,
we are requested to go outside next year. Do you know about that?
No, I did not know that.
Okay.
So
and probably, I don't know if you noticed, in China was not quite tricky, but even if you don't have sunlight, normally, even due to other leagues, you have very strong lights on the top, on the ceiling, which means that you have such an open aperture in the vertical, probably you'll be flooded with that light.
Oh, okay.
It means that you have to take that into account. Yeah. Maybe you cannot even see the ball if it comes from above because there is a bright light in the background. Okay? So I'm not quite convinced yet that this will solve your problem of not seeing the balls that go above. But I think it's a really nice strategy that should be tried out, and you should share all the information you can about that with us in the future. I hope you the best regarding that attempt. Any other questions?
Basically, not a question, but you had a question regarding the simulator. Can you switch back to the slides from the simulator and architecture? Yeah, more or less. About the simulator, you want to switch to Ubuntu 14.04 and take ROS Jade, and yeah, okay. And the last point of this slide is using a simulator based on Gazebo. We also try to implement a simulator based on it, and some research. We saw that the simulation league, or not the simulation, the small size league has already a simulator in place for their small size robots, and it's called GR-Sim. And in the core, it's already based on the ODE, Object Dynamic Engine, which is the physics engine of Gazebo. So there is already, it's open source, and there's already a lot of source code you can take, because they're robots which they already simulate, just a small one, but they already have an OmniDrive and a kicker, and so these are basically actuators you want to simulate in your simulator too, so you can adapt the source code and just size it up to the size of your robots. But currently, we are not ready or didn't even start with the real simulator we want to base on Gazebo, but currently we are using an adaptive GR simulator from the small size league to bridge the time.
Let's follow up on this during the coffee, because I'm interested to hear more.
Yep. And also one interference is, for example, in ROS you have Gazebo integrated more or less, and just after the version of Jade they used Gazebo 5.0, so if you stay with Indigo you're forced to use Gazebo 2.0, so they make a big step forward from ROS Indigo to Jade. So
yeah, that was one of the reasons we also migrated to Jade. Yeah.
So we also think about that. So we are basically in the same boat.
Okay, thank you. Thank you for your presentation.
Thank you. And I think that before coffee break, our girls are preparing the coffee break in the back. Okay, I'm joking. I meant no disrespect, neither to you, neither to any girl, okay? Just joking. Okay, so next we have the presentation from the mini team.
Hello. Yeah. Good afternoon. We are Minho team. I'm gonna start to present the of Minho. He's also team leader and our chief engineer. That's me. I'm Elder Ribeiro. I'm I'm working on artificial intelligence, tactics and strategy. Pedro Osorio is working on vision and calibration and 3D ball recognition and the goalkeeper. Tiago Maia, motion dynamics, motion planning. André Gomes, power electronics and hardware. Ricardo Roriz, RTDV communications. Nuno Ferreira is our mechanic, ball reception mechanism and mechanical engineer. Media team started participating in a very long time ago, but we have stopped about 2011. We have participated there in Istanbul, but the robot was not working very well. I think we can't compete, can't make the whole game. That time the robot was stopped. That we have a lot to work on it. Now it's starting to working. We have until now we are just working in the hardware because we have a lot of flaws. Last year we think we will start working on the software, but because of the hardware was not stable, so everything we do doesn't work well, so we have to renew all the hardware, and now it's starting to get it somewhere. We are not going to present nothing very special, just how we renew our hardware. We are just here to learn from you and to start to see what you are doing and not making the same mistakes you are doing, just learn from that. We are using a point gray camera, Blackfly. It's a new model, GKE. It's from Ethernet. It has a simple lens. We use the curved mirror like you, I think, all of you. And we use a UMU, 9 degrees of freedom, just to get the rotation and all the axis. We have the robot divided in layers from bottom to up. There are 3 layers. The bottom layer is the layer where we have the batteries, 2 batteries, 12.6 volts, 4040 milliamperes. Have 3 Maxon motors, plus the gear, the wheels and the encoders. And we have a omnidirection motor controller. This is developed by a former student who worked on these robots. Now they have a company, they have started a startup company. You can buy this board. This is optimized to these motors and to this type of robot. In the second layer, we have the hardware who controls the kicks. You have the kick capacitor, the board who controls the charge and discharge of capacitors, the inductor to the ball. So we can see if it's 1 meter, 1.5, it has a good resolution, and it can help the visions to give an extra sensor. It's very simple, it's very cheap, so we use it. This is the box we have made. You have all the hardware to control all the robots. You can see there it has all the connectors. We try to make different connectors, so in the heat of the game we want to switch the connectors and make a bad connection, and then won't work. We are trying to make like Arduinos. They have that type of layer, so we can always be having new hardware to this. We can remove this one or make a plus one, and all will work together. Right now we have 3 microcontrollers, 3 ATmega 328 to control all the hardware. In the final layer, the 3 layer, we have an inductor who controls how we kick, if you kick straight or if you kick with effect. And we have our power box. It controls all the power. We have that buttons to disconnect everything, like the motors, the kick, the controller box. We can switch off everything from that. It's accessible, very easy. To control all of this, first we have to use this one. These are PCs produced here in Portugal. They are very weak. They don't have any power of computer, and we have to get rid of them. One of our professors suggests that we use this type of board. Because we are using the point gray, to get its SDK to get the image, but they are not producing the things they have to give us the image were not made for ARM processors, so it kind of don't work well. That type of camera should have 13 FPS. With this board we only can get 2 or 3 FPS because of some problem from them. We try to work with them, but it doesn't work. They don't know well. They are developed on the fly. So for that we have to change to a normal PC, a mini PC. It has an Intl inside, a dual core. With this we can have the 13 FPS and we can work it all well. Now Pedro will continue the presentation.
Hello everyone, I'm the vision guy, the guy who treats the vision, and like everyone, we have an image acquisition from the Ethernet camera. Then this is not to show how we do or to teach something. It's to show you our mistakes and to hear from you what we can do better to end up playing. And so we get the image, we make image processing to detect our line points with radial scan lines. We don't perform segmentation in the whole image. We are just performing segmentation on the radial scan lines because of the low power of the power processing of the board. Then we get our heading angle, which we trust 100% from the EMU unit. Then we perform an error minimization locally or globally. We are now rebuilding all of the software, and of course we don't really have been testing this. Now we didn't in Robotica in Villarreal. We only have global localization, which performed at about 25 milliseconds to search through every position of the field, and that's not acceptable, of course. And we experienced some jumps and errors, of course, because we didn't use the odometry, which now we will be using a common filter, of course. This is our image. We have been getting some problems. You can see, I can point this, okay. Here we have a blurry image and many image problems. Here we don't see these lines, and this is not the official field. This is the field which we have in our lab, which might be like 1/4 of this field. So, and we can't see that great. But anyways, we are trying to fix that. So we do this scanline search. I guess everyone does the same in a different way, but the same. And we detect the line points. Then we try to estimate our position using only 72 radial scan lines. We will try to make more lines to generate more points. And this is where I guess we are making a mistake. We are comparing these distances with pre-generated distances from every point of the field. We are looking now to the perfect match of 3 bots to see how they do it, because I guess it's a better way. Like I said, we experienced many jumps from the position estimation. Like we are in this corner, and then we jump there and back and there and back. And that can't be an estimation. So we are experiencing a lot of exterior light interference, and we saw on Kambada repositories the self-calibration for the camera parameters. We are looking in that too, and we are looking at, of course, in calibrating well the segmentation, etc. This is our, you can see our light problems. In our lab we have a very low height ceiling, so we have a strong light hitting the middle of the field, and we have this problem where the green part of the field becomes a line too, and the ear too. But with Elder here and me here covering the lines, we still were able to locate using global localization. We have a short video here showing what are we doing. We are searching only for the first line point. For that, because the way we choose to calculate our position is we have a pre-generated file with a 10 by 10 centimeters resolution, where we say at this point in the 72 distances we have in degree 0 you have a line at 1 meter, in degree 5 we have a line at 2 meters, and with this we get those meters and search on that file where we have the least error. We are making that, I guess, bad because we have to make many calculations. We are now looking at the way that 3 bots do that calculation. We can see the red points, which are the lines, the blue points, which are the obstacles, black parts of the image. And I'm also making the Kinect. Podes coisar isso? I'm also making the Kinect recognition part, where we'll be doing it in the goalkeeper, the only one who will have a Kinect. We acquire the image using their API. I don't know, you use it too, FreeNect, and we acquire the ball, we use the color image to get, you can see this Santa Claus here, which is red too. And it will be my jacket and other stuff that is interfering with our candidates. But we then perform some, how can I say, geometric comparisons between height. We are not doing that here. At this time we weren't doing. And we are mapping the pixels into the depth image to see what is the height of the ball, the distance of the ball, the real distance, and the 3D coordinates. And we, okay, like I said, and we'll be trying to use this to predict the ball movement and to know where it's going to go across the field line, the goal line, like here, and to try to defend the ball, not to let him go inside the goal. Then before I step into this, I will be finishing the localization part and all the vision, and then I will try to make, how can I say this, active goalkeeping behavior, where the goalkeeper just doesn't stand in the middle of the goal. It is what is like now, and based on the human goalkeeper behavior, and of course building a goalkeeping structure with arms, I don't know, because we don't have any. We have 5 robots that are the same, and one of them is the goalkeeper. And that's it. Thank you.
So first of all, let me congratulate Minho for this huge effort for after so many years, let's say, making this comeback that I hope will be successful in a short time. And of course, one of the first questions here, there is a lot of things going on.
Yes, at the same time by the same people.
Yeah, you said yourself that of course you are going through a rough path with finding new problems, some of them old problems actually.
Yes.
And of course I hope you can take the most advantage of being here with people from so many different teams that can maybe help you with that. And in terms of expectations, do you have a target time regarding bringing this all together and putting it
we are wishing to end this whole problems, like I said, finished later on until January, I don't know, maybe the end of December, and start making some real game software. We started coding. I started coding last week only, because we are all rebuilding the robots, and that's kind of sad. I don't know. And we target to really try to play like we didn't do in Robotica last year. We will be trying to play a game. I don't know, start it, maybe finish it in Robotica, and if everything goes well, in Dutch Open and RoboCup, of course.
Dutch Open will be before Robotica this year.
Okay.
1 month earlier.
Okay.
Yes.
So
probably if you have the chance to go to Dutch Open, you should. If you have possibility to play, of course.
If the robots play, we'll go, I guess.
Yeah. Okay, you mentioned something. You have been rebuilding the robots, right?
Yes.
Fixing all the hardware problems.
Since September until last week, we only solder, tight bolts, that crappy stuff.
Okay.
We are start coding now. Let's see what happens.
And are you convinced that you have solved at least the major hardware problems?
I guess so.
You guess so?
Okay. Before Robotica, some of our motor controllers burned completely, catch flames, and I hope we don't, like your robot in Robotica, and we are hoping that doesn't happen now. And we wanted to do this because we said to each other on the team, let's stop everything we are doing, let's rebuild this, because we can't work with an unstable platform, and that was the decision to be made.
It's a very good decision, I would say.
Thank you.
So there are any questions regarding Minho? Yes.
in fact, as you could expect, it's not a question, just more a comment or so. So this is a good chance to restart the team, as you know, it's many years. I'd like to point out that they are not PhD students or master students, they are undergraduate students. And we work, like the Falcons were saying, they work extracurricular. It has nothing to do with lectures or anything, or any work related with the degree. But yes, since Villarreal, I guess the robot now is stable. We've been doing some tests and really stable. So it used to be stable with different generations, right, a few years ago. But now I guess it's, in my opinion, it's much better and it's stable. So it's time to start the software, and this is like a good chance to learn something and to start developing the software the proper way.
So many more questions, comments? Okay.
I want to come back to, you showed us that you only detect the first line on each scan line. When I look, for example, at the placement of that robot over there, and let's say that you don't see the circle because you cannot look that far, then you would receive a lot of ambiguities if you only look at the first line point. Whereas if you would also detect the second line and the third line, it would be much easier.
Yeah, we know that we are only looking for for the radial lines. We are missing a lot of points. Like if we are here, there's no difference of being here or there. It's the same thing. Like there, if we have both line points of the area and the goal area, we have more points. Okay, we are looking into that. That's our way of doing things last year. So now we are looking at what we have done, our experiences, what is wrong, what is not wrong, and we are trying to bundle everything to become to get a working localization and vision.
I think you missed Andre's talk last China, but we actually created something called spiral search for localization, where you can actually even filter out the white spots you're now seeing, like some US share.
Okay, thank you. We will be talking to you on coffee break. Yes, yes, yes.
I think I have the presentation somewhere on my laptop, so we can run it through if you like.
Thank you.
I think this is a very good suggestion, of course. I immediately remember your presentation in China when I saw that image. Exactly. And your spiral solution is really nice because it is an integrated solution of radial and circular sensors, let's call it, okay? And so it's very interesting to look at their work, and probably you can gain also from that experience. Okay, any more comments? More questions? Are you ready for coffee break? You are ready. Okay, the question is, are there coffee there? Is there any coffee there at all? Okay. So probably we'll take some time before a presentation from Tech United and have a coffee break, have some talk, some mingle, and take advantage of it. So are you ready to restart? So next presentation will be done by Tech United. I hope a lot of nice stuff will come out of this presentation.
Is it on? Yeah. Did we activate it or not? No. Okay. Doe dat maar.
Hi, welcome everyone. I'm Lotte and I will do this presentation on behalf of Tech United together with Koen. We want to show you our planning towards RoboCup 2016. These are three main points we are focusing on this year. Starting with replacing our Kinect cameras, all of our robots, field players and goalkeeper now uses the first Kinect. We are aiming to replace them with Kinect 2. Secondly, I will move on with shooting at goal, improve the efficiency on goal, and finally improve the gameplay to make it faster. Now,
Thanks. Welcome. I will present something about the Kinect 2, as Lotte just said. Does this work? Let's switch it on. Ah. Okay. So currently we are using the Kinect version 1, so the Kinect of the Microsoft gaming thing, Xbox indeed. And we use it on to see balls, so not to observe obstacles or detect obstacles, but only to see the high balls. We have mounted the Kinect on each robot, and we have actually mounted two on the goalkeeper to have a wider view angle. But there are some shortcomings on this Kinect. And the first one is that the CCD has quite a low sensitivity, which means that if there's a lot of light, we can set the exposure to a low value, and we can get images up to 30 Hz. But normally when we play in championships, the light conditions are not that good, and we need to set the exposure to a little bit higher value, and we can't run at 30 Hz anymore, and we get less images. Another issue is that the CCD has bad colors, or bad quality colors, so the color level is not that good, which means that calibration of the ball is more work and is less stable. So that means that sometimes when you calibrate just before a match, that during the match the light condition slightly changes and the color, the color is also, the color calibration is also degraded, which means that it's more difficult to see the balls during the complete match. We have some stability problems, mainly in the connectivity, which means that, for example, we cannot start up one of the streams, or during the game it's losing connection. And the depth range is limited to 6 meters, so I heard higher numbers from, I guess it was Minho. But we can see balls up to 6 meters. And that is not so far, because if the ball is moving at a high speed, or 10 meters per second, for example, like when we do a full shot, or when water is shooting at our keeper, the ball will have a speed of about 10 meters per second, and that means that we only have 0.6 seconds to actually react after the first feature that we see. So that's why we start moving to the new Kinect. So there's a new Kinect camera, Kinect 2. It has a higher quality CCD, so it's more sensitive, so we think that we can always run at 30 Hertz, so we don't have to downscale it anymore. We have a better color quality, so the color images are much better, which makes it much easier to calibrate, so maybe calibrate only once during a tournament. We hope that we have less stability issues, that connectivity is better. We did some experiments, and we can adjust the depth range to see balls up to 9 meters. So that's the complete, the complete half. So that should be sufficient. And we have an increased view angle. So maybe we can replace the 2 Kinects on the goalkeeper by only 1, or at least each robot has a better view angle, or we mount it on the robot. One drawback of the Kinect 2 is that it has a different way of capturing the depth images, which means that you require a GPU to process the images. So before we could process everything on our own CPU, so on the computer of the robot. But now we have to switch to a GPU, and our robot in the robot is a back of industrial PC, and it doesn't have a GPU, and it doesn't have extension possibilities for a GPU. Yeah, there is you can add a big bracket on it and put a GPU, but that's not sufficient, or that's not what we want. So we are looking at something else, and it's a Jetson TQ1 development board. That's a development board which has an NVIDIA chip on it, so an NVIDIA GPU. And these are the specs. So it has an NVIDIA Kepler GPU with the 192 CUDA cores, and it also has an ARM Cortex on it. So we have, I think actually we have 2 or 3 ARM cores which are close to connected to the GPU. So we can run, for example, 4 cores. Okay, so that means that we can run Linux on this board and use the GPU to offload the image processing, and we can program it using CUDA, so that the image processing is programmed by means of a parallel language. The connectivity it has a USB 3.0 connector for the Kinect, and it has a gigabit Ethernet LAN that we want to use to connect to the robot. So how do we want to detect the ball? So first of all, we want to do registration of depth and color image. That means that we are mapping each pixel in the image. We map the depth image on the color image, or the other way around. So what we do, we have to remove the distortion of the lens, which you have in your color image, and then you can map each pixel so that you have, for each pixel you have depth info and color info. Then we use color segmentation, use the Google annotated database. So in the database, all the colors are defined. So if you say, I want to have all yellow pixels, then it makes a map which says, okay, these pixels are considered yellow by Google. And that works pretty well with the new Kinect. The next, we do a flood fill algorithm for blob detection. And then we select the blob based on the size and distance ratio and the width and height ratio. So we know the size of the ball, it's circular. So we know the ratio, and we know the ratio. And when it's further away, the size in the image gets smaller. And the last step, we do the transformation to the robot's coordinates. A little bit about the implementation that we have at this moment. So we have the GPU. The GPU is doing the JPEG decompression of the color stream, and it's doing the depth reconstruction from the infrared phase images towards the real depth picture. So the Kinect 2 has a time of flight principle for making the depth image, and that's what we run at the GPU, and also the flood fill on the GPU. And at the moment, at the CPU, we're doing the registration, so the mapping of the color and the depth pixels, and we want to move that to the GPU using a CUDA. And the color segmentation is also in the CPU, mainly because it's working fine, so we don't need to move it to the GPU. And the blob selection is also running at the CPU. The results so far, that we were able to detect the ball at 30 Hertz. And the accuracy is still unknown because we did measurements with the Kinect, but we didn't have a second sensor as a second source to validate the measurements. And I have a movie of it. You see here the red box which annotates the ball. And when you move the ball around, you see that it's capable of tracking the ball quite good. So this is a standard yellow ball that we also use during tournaments.
That's some Portuguese coffee, right?
Sorry?
Yes, some Portuguese coffee.
I'll show it again. No? I won't? No, so what we do, we capture an image, and then we try to couple the depth info to the color. And if we don't have depth info, we remove the pixel actually. Then we do blob detection, so we look for yellow blobs. And then we use the depth information to see how big the blob should be if it's considered to be a ball. I'll show it one more time. So on the top left you can see the distance with respect to the camera, how far the ball is from the Kinect. So not 9 meters yet, but yeah, up to 4 meters it's working quite well. So some future work. What we did for the Kinect version 1, that we implemented the tilt compensation. So the Kinects are not mounted very sturdy on the robots, which means that they can, yeah, if there's a collision with the ball, that it might move a little. So that's why we use compensation. And how that works, the Kinect is also looking at the field, so it tries to fit the plane, which is considered to be the field, and with respect to that plane, yeah, it can compensate how it's looking forward. So what we need to do, we should move that implementation to the Kinect 2. And besides using it for ball detection, we also want to use it to detect obstacles. So far we use it mainly on a keeper, and there the main priority was to see balls, but of course it's also a very nice sensor to use for obstacle detection. So that's the next step. We want to remove the field from the registered image, and everything that's left is actually or the ball or an obstacle, which then can be an opponent or a peer, but that's handled by the world model. So then we get more information from Kinect 2 than just balls. And in the far future we also want to do some line detection and also the goal detection. So instead of what we do right now, we check where we are, and then we know where the goal is, and then we are going to shoot at the goal. But we might think that we get some more accurate shots if we actually look at the goal, so look where the goal is. So if it's moved slightly to the left or to the right, that we can actually shoot in the goal instead of shooting at the position where the goal is supposed to be. One more slide about communication with the Jetson that I think is nice to tell. So as you probably all know, is that we use the Kambara communication with RTDB to communicate between the robots. So how does it work? We have an RTDB database on the robot, and here we have our 3 executables or processes which are running, and they all share information with each other through this database. And then we have another process which is the comp process, and the comp process is reading the records which are marked shared in the database and sending it over Wi-Fi to the other robots. And that's also what we want to use inside the robot itself. So we have the Jetson board, which is connected through LAN, local area network, to the robot, and we want to use a second comp process on the robot PC, and also a comp process on the Jetson board, and then communicate through that comp. Let the 2 RTDB databases communicate with each other. Because we think that's a flexible inter-process communication. It's easily extendable, so you can share information from the robot to the Jetson board and vice versa. So if the Jetson board needs, for example, the position on the field, so where the robot is, it can also get that. Well, this we can easily do with the RTDB and the communication as it is right now. So we only have to adapt the COM slightly, that it also works on that it can that you can select a second Ethernet connection or a second IP address. And what we are thinking about, maybe possible performance or reliability improvements, is that instead of sharing all information to the Jetson board, because we can mark the records either local or shared, which means that all the information which is also for the other robots is now also sent to the Jetson board. So we think about adding a new record which might be called remote or something like that, so we can send only a subset of the records to the Jetson board. Another improvement might be to use TCP/IP instead of UDP if we think that that's better to communicate to get it more reliable, or to make this communication process triggered instead of fixed rate. So at the moment we run this communication at 40 Hertz. That means that all robots communicate at 40 Hertz at a fixed rate. But maybe on a Jetson board it's much more interesting to actually trigger the COM to send data to the robot when it just acquired a new image and get the balls, and then just sending the data directly instead of waiting for a new cycle to end for the communication. So far about the Kinect 2. Are there any questions already, or shall we just proceed with the second part? Yeah? Yeah?
How do you choose the seed for the
Sorry?
How do you choose the seed?
Ooh, that's I don't know.
Second question, please. How do you validate the ball? Just for the size relationship, or do you use information from the depth to validate information?
Well, we calculate the size that it should have based on the distance. So we check how far it is away, and then we know what the distance it should have in the image. So that's one thing. And another a rule that we use is the ratio between the width and the height. So it should be circular. So those two steps are currently used to say whether it's a ball or not.
Do you remember Brazil?
I remember Brazil, yeah.
You remember the venue that has those yellow things on the top of the building?
Yeah, yeah.
So that led us to a solution for this kind of problem based also on the depth information.
Okay.
I strongly suggest you to take a look. We had a paper in this year in Robotica.
Okay. Good.
Because this is really a problem, it was also for us. My third question is related to the black information that you have on robots for obstacle detection. I think that should be also a problem. So I would like to see a result also for that. At least with the Kinect version 1, you cannot distinguish, for example, the black information from the robots.
Okay, yeah. I think it worked on our robots, but I can imagine that many other robots it won't work so well. That's true. We are still in the first step, so we are using it now for ball detection. But indeed, we know that but maybe the new Kinect with the new way of making depth images. So instead of structured lights, it uses time of flight. So maybe you get better results with that. But yeah, we didn't investigate that so far.
Okay, thank you very much.
Okay. Yeah.
I have a question about latency. Do you have any figure about latency from the real ball movement until you get the information into the CPU?
No, we didn't measure that yet. But I think because the Kinect is quite fast, it's not that significant. And something else, it's not a big issue. So what we see is that it is fast, and that might be enough. Because what we do, we use it mainly for checking the direction of the ball. So if we see the ball is flying through the air, the only thing that we are interested in is what's the direction, so that the goalkeeper can stand over there. And it's not interested when it actually hits the goalkeeper. It's just that the goalkeeper should go there as fast as possible to make sure to block the goal. So it's different than intercepting a pass, for example. Then you might want to have more information when the ball is where. But here it's sufficient to know where it enters the goal.
Did you give a rough number, like 100 milliseconds? Or?
No, I can't.
I'm not up to date with the Kinect. Is there an open source driver for it?
It's I think the LibFreeNect has a new version, which supports the new Kinect, and that's also actually why we need to go to a GPU. So I think the water team is running it on the CPU because they can run Windows. So there is a Windows driver available, and I think with the Windows driver you are capable of running it on the CPU. Okay. But with the LibFreeNect you can run it on a. You need the GPU to get it working.
And GPU means NVIDIA and not Intel integrated graphic card?
Just a GPU is fine. So the processing power of a CPU is not sufficient.
Okay.
So if you can run it on a FPGA, it's also probably also fine. But
sounds like you would have problem with an Intel integrated graphic card. You could.
No, yeah, but the integrated graphics card inside our industrial PC is very weak, so you can't actually use it to program to process images. It's because you also need something to offload your image to that video card, of course.
Well, the problem with the Kinect is the influence of light. So if you have lots of lighting, it doesn't work that much. Is it still true with the Kinect 2? Have you tried with different lighting, or it works? Do you still get the 9 meters, or does it reduce with lighting?
We didn't make it very difficult for it. So we used different light conditions, but still it was always inside. So still like in an office. We didn't check with extremes, so we didn't make it very dark or very bright. But everything seems to be better than the Kinect 1, and especially with the depth image is much sharper. You could see that the resolution seems better, less noisy. So it is better, but numbers how good, I don't know. Yeah.
Okay. Any other questions? Let's move on.
Yes? It's good? Okay. Okay, I will move on with improving our efficiency with shots on goal. So after the last RoboCup 2015, we evaluated our final matches, semi-final and final, and we came to the conclusion that we had a lot of goal attempts, but few of them were successful. In the semi-final, 29%, and even in the final, 7% successful goal attempts. So there is some improvements possible there, and we made an analysis of the kind of shots on goal, what the cause was, why didn't they end up in a goal, and these were the solutions. Well, mainly the first one, improve the lob shots, and the second one is what we already were working on, presented it during the scientific challenge, and I shortly want to show you how far we are or what we're doing now. Yes, but first improving the lob shots. Our current lob shots are mostly used to pass over an opponent at goal, but most of the times it's a weak shot at goal. We are using a shooting lever, which can be used at many different shooting angles, but we are now currently only using 3. One for just a pass, a simple pass, one for shooting straight at goal, and one for the lob shot, so the maximum shooting angle of 45 degrees. And this results, yes, in a low velocity, so a weak shot at goal, and we want to improve this, and our goal is an accurate lob shot with an adjustable shooting angle, so that the robot can choose which shooting angle is the best for a nice shot on goal. And this is how we did this. So we had a ball model, we already had that, but validated it for a bouncing ball. And after that, we determined a relation between the ball trajectory, so where the ball ends up for this bouncing ball for a lob shot, and the lever setting, so the shooting angle, but also the initial velocity. And finally, inverse this problem, and from a desired target, get the initial conditions for the lever settings for this shot. So first a short movie. Some of you already saw it during RoboCup. we have a ball model. This is a bouncing ball shot by a robot, and the red line, and now the blue, or the green line. So this is our ball model, which is pretty accurate, and this is what we used. And then we did experiments. So we had all our robots shooting shots at the goal using different settings for, well, in this case K and L. K is our kick effort, so the duty cycle we send to the PWM module, so for the shooting velocity. And L, the lever settings, so the angle of the shooting lever. And we got all of these kind of graphs where we have a ball trajectory. And in this way we had a relation between this ball trajectory and these lever settings. And so the final step was to inverse this problem. And this is the result. And here we use this green board in the goal with 2 holes. And those holes are our desired targets. So we want the ball to enter that hole at the highest point, so with the highest possible velocity. And from different spots on the field, the robot shoots the ball. So we have 2 examples from this side. And you can imagine that such a desired target is the upper right corner of the upper left corner of the goal, and dependent on the position of the opponent you want to pass over and your position on the field, you can now calculate the perfect settings. And we hope to increase our efficiency with this. Well, then the shooting with effect. For those who didn't join RoboCup, I have this movie of a project one of our graduation students is working on, and the goal is to shoot with effect, so to give a certain spin to the ball, and when the ball bounces on the ground, the direction of the ball changes, so like this. The ball is spinning in the air, and now it's, so this is an animation. We're not there yet, but this is what we have for a goal. And this is how, so he first made that a ball model estimation, like I showed before, and he inversed this problem. So now, and this is already how far he got. So he has, for a desired target, he knows what initial inputs, which parameters he should adjust for this. And now he's working on the 3rd bullet point, which means that he's investigating with different experiments how we can add spin to this ball. So in what ways you can do it. Well, our ball handling uses small wheels. You can use those wheels to give a certain spin to the ball, but also using the position of the shooting lever. So not shooting ball off center, so shooting, hitting the ball off center. And he's now investigating, he just started with that. So I unfortunately don't have nice movies or pictures of that, but we will certainly share them if we are this far. But hopefully, the goal is in Germany. Hopefully, we can show we can show this to everyone. Okay, then the final point we are focusing on is the faster gameplay, and this is related to our strategy implementation. We're now working with different roles, and those roles have certain tasks or actions they can perform, but not each role can perform every action. So, for example, a defender catches the ball because he's defending an area. He gets the ball, but he's not able to make a pass to an attacker which is far in front. But instead of that, they switch roles. The defender becomes an attacker, and he goes to the opponent's field side to make an attacker of it, to make an attack. And at the same time, the attacker becomes a defender, so goes back to our own half to be a defender. So you get those role switches, and you see that this happening on the field, and it's not very efficient. So those are the limitations. The actions are limited per role, and that's not what we want. And the state is not preserved during role switching, so when he goes to a new, when the defender becomes an attacker, it gets a new role and it starts all over. So this is how we want to implement it. No behavior implemented in roles, so each role should be able to do every action, and the only roles we end up with is 2 defenders, 2 attackers, so the robots are nicely spread over the field in a smart way. But if the defender gets the ball, he can immediately pass the ball to an attacker on the other side of the field, so we have a faster gameplay. And we can implement sequences of actions, so the defender can really think of, okay, I play the ball to the attacker, and the next thing I'm going to do is also go to the other side of the field for a free spot to so he's in a scoring position, for example. So these sequences were not able before because of those role switches, and you had to start over all over again when you switched from role. So these improvements will enable this, and we are aiming to play in this way next tournament. And that tournament will be in the Netherlands. So this is a promotion slide. We organized the European Open in the end of March, beginning of April. Hopefully you can all manage to be there. A nice tournament to practice. It will be in Eindhoven. I'm part of the organization committee, so if you have any questions about it, then please ask. Thank you for your attention. I'll put this on. Any questions?
Yeah, that's the question.
Yeah.
Okay, lots of new stuff that we're hoping to see in maybe Dutch Open first,
yes.
And then in Germany, hopefully. And so let's hear from the other teams. Questions?
Okay, so my question is regarding your behavior switching and role switching. I don't think it's a good idea to have global actions or behaviors, as you call, or action. You call them actions, right?
Yeah, an action like dribble, passing.
Okay, so high-level behaviors. Because sometimes, at least in our case, there are dependencies between actions, and those dependencies are related to the role. And you can have, for example, one action like dribble, for example, but you want to make different dribbles on different roles. For example, And if you are going towards a solution where you have every type or any type of behavior or action, you will end up with a huge list of actions to do. Or you have a simple list, but you don't have that configurability. What I'm asking is, have you considered any kind of relation between actions inside the role? Are those configurable? Yes, no?
I think Koen can better answer that question.
It's not necessarily that each role can execute any action, and it can be that it's not said that an action has not parameters which depend on the role or position on the field. So of course, you can provide information to the action, which is dependent on what kind of role the robot has, where he is on the field. Indeed, maybe he doesn't want to dribble so far if he's a defender or an attacker because he should shoot at goal. And I don't know. Yeah, we don't know whether that's really role dependent or maybe more position dependent on the field. But it is configurable.
Yes, my concern is that when you change the same instance of that action on different roles, you are influencing one role with another one. That's my concern. But just a comment.
Yeah, that might be indeed. Yeah. Thanks.
More questions?
Regarding the efficiency of the kick to the goal, how did you manage to deal with the velocity of the robot? Because you provide experimental results showing the kick to those holes, but when the robot was stopped. What is the effect of the robot movement in that procedure? And you managed to estimate correctly the velocity of the robot and use that information to perform a better kick?
So if I understand it right, you mean the movies I showed, the robot was standing still, and what happens if the robot is moving and then adding a kick. In this project, it wasn't taken into account, so the robot was standing still, but now someone is working on indeed the dynamic lob, so if the robot is moving. So I can't tell you right now what
I'm just asking because you said in those topics that was green, that one of the things that you took into consideration was the initial velocity. So that is why I'm asking how you do it and how good is that estimation?
So yeah, what we now only did is what with a still standing robot. So we didn't deal yet with the driving robot and then shooting.
Thank you.
Although Koen wants to say something about it.
We do have compensation when the robot is shooting with a flat shot at the goal, but not for the new lob shot. What we do, we take into account the robot velocity. So, for example, if he's driving sidewards, we take the initial velocity of the ball, which is moving along with the robot. We take that into account. And for example, if we move to the right, then we aim slightly to the left, that the ball will end up at the correct position in the goal. But that's something we already had in Istanbul, I think. So that's not new.
Sorry. Still regarding that improving lob shot, do you have any results regarding the repeatability of what you can get? Because I remember you said that regarding those two holes,
yes.
The idea was to shoot on the top of it.
Yes.
The second one, for instance, enters on the hole, but on the bottom of it. So my question is, what is the level of repeatability that you can get from your estimation, basically? Because balls aren't round. So you may get a real nice model of the ball, but the actual ball won't be exactly that one. So
you have any results on that?
Well, for the experiments of the movies I showed, there were 2 examples, but the student did those repeatedly, and for example, 9 out of 10 were into the holes, like.
Okay. Did you try to reduce the size of the holes?
Not that far yet, but as I said, we want to use this to shoot very accurate in the goal, and that's what we're now working on. So implement that in.
Your hope is that your level of accuracy in terms when playing against water will increase significantly, right?
Yes.
Any more questions regarding any of the 3 teams that were presented by Tech United? Oh, okay. Thank you so much again. Now I'd like to invite Wouter to present the work he developed here in our lab in the past couple of months.
No? Yeah. Yeah, great. Yeah, so I'm Wouter Kuipers. I'm from Eindhoven University Technology, just like Tech United is. And I'm doing my internship at the university here, more specifically at the Gambara robotic soccer team. So what I want to show you in this presentation are the results and the process I did in my internship. My internship is about 3D ball positioning. I will tell you a bit more in the start. Then we go to some challenges, how we solve them with an actual triangulation algorithm, the results for that triangulation algorithm, and then I will end with some conclusions, some recommendations for implementation. So the target is to develop a 3D ball detection system for robots in the MSL League. So several solutions have already been presented, also today. So for example, adding another perspective camera, using Kinect cameras. There are also some things, for example, with the bijection principle applied to the projection of the ball, which makes that actually every projection is unique. And in that sense, you could also estimate the 3D ball position. We're actually interested in a more in another totally different method, I would say, which is focused on cooperative sensing. So my assignment was to research and verify whether this cooperative sensing can actually be used for this purpose. So how does this look like? We work with the triangulation of OmniVision camera data. So we have 2 robots which both make a projection. In this case, robot 1 makes a projection at P1, robot 2 makes a projection at P2, and in the most simplest case, crossing those lines will give you the 3D ball position. This ball position can in the end be used to, for example, give a better estimate of the ball position actually on the field. So in this case, robot 2 will not say that the ball is at this position, but will actually correctly find the position P ball. But also this height of the ball can, for example, be used to design an interception strategy for lob passes. So this has some challenges. I listed here 3 of them. So the first challenge is, for example, that due to noise or inaccuracy, the lines of sight of the robots do actually not cross. Well, this was already solved in a previous research. It's just we're not looking for the actual cross point. We're more looking for the minimum distance between the 2 lines of sight. And then on the midpoint of, of that minimum distance line, or maybe another weighted average, you could say that the ball is located at that point. That's already solved, but the more challenging part is actually the communication between robots, because we need to combine OmniVision data, and this requires communication. So in this case, we have first one big challenge, which is the communication delay between robots in the robot-robot communication. So as you can see in the second figure, for example, if the pink robot is the actual robot we are, then the data from the peer robot, the red one, will not arrive, it will arrive, for example, after 3 samples. So how are we going to treat that? In a previous research, there was a solution for this, which said we will just extrapolate this projection data up to, in this case, ti plus 5, which is actually like the moment we are currently evaluating. However, in some tests, we found that the communication delay plus some added noise might create a huge inaccuracy. So I came up with another solution for that, which I will present in a moment. Then there is another challenge, which is actually the limited amount of data we get from robots. For example, the robot itself could have some time instance where the ball is not visible because it's, for example, blocked by another robot, or it's just somewhere else on the field. There could also be, in the case of the Gambara team, they do the robot-robot communication at 10 hertz. So, for example, these could come in like every tenth of a second. How to handle that? I will explain that after I presented this MATLAB simulation environment, which is part of a previous research and some additions I made to see actually the effects those previous presented challenges have on the actual triangulation algorithm. So for that I needed more robots. So in this case you see 3 robots, a green one, a red one, and a black one. They are communicating with each other with a variable communication delay, so it's not constant, it's all over the place, so to say. The robots can actually have a clock offset. So, for example, if we timestamp the data, then measurements taken at the same time, same global time, I would say, can have a totally different timestamp because of this clock offset between robots. And then there is this package loss, which is challenge 3 on the slide I presented before. So these all are implemented in the simulation, and you can actually see in this visualization that there indeed are some places where there is, for example, one packet lost and there is a lot of noise on the projection. And in this case, the blue line you see is actually the ball as it's detected by the 3 robots you see over here. At this point, the ball was bouncing, it was shot by the green robot, and the green robot is driving behind it, and the red and the black are driving alongside it. Also, I implemented a different ball model just for the sake of being able to simulate both the bouncing dynamics and rolling dynamics. This means that actually the ball model is not only containing continuous states, it didn't actually when it was a bouncing ball, it also had discrete cases, but now it actually has like 2 different parts of the model which are switched between. So then for the triangulation algorithm, so suppose we're now at time tn. To solve the problems, or actually the challenges I stated, the following solutions we came up with is that actually with the communication delay, we want to tackle that in the way that we're actually not evaluating tn, but we're actually evaluating the moment in time when all the data, or some set of data, has arrived from the other robots. So in this case, tn minus 4, that's, for example, a moment where all the data from all the other robots, say there are 3 at the moment, that all the data has arrived. Then we perform the triangulation on that time instant, and we filter it using a Kalman filter. And then actually we're going to, we need actually the ball position at this moment, so we just use the model of the ball to go forward in time. Instead of using, for example, extrapolation to extrapolate the OmniVision data to TN, we use a ball model to go forward in time. So it's like a little bit of a switch in there compared to the extrapolation approach. Then as a third, the solution to the third challenge is to combine the line of sight we have from the robot with the actual predicted position for that moment of time by the Kalman filter. But I will get back to that in a moment with a bit more detailed explanation about that. Because in a moment I want to continue with an explanation of the algorithm itself. The algorithm consists of 4 main parts. You can also see them right here. It contains a data buffer, it contains a Kalman filter, a triangulation, minimum distance algorithms, and it consists this part which we will for the moment call model update. So then to start with, to give you a bit of a feeling how it works, this is the data buffer part. So we start at label number 1. First we update the master clock, and this is actually a graphical representation of the data buffer which is in the algorithm. We see per column the robots, and each row represents a certain time instant. So for example, currently we will be in robot 1 because that robot has the latest data sample. So this loop on the left fills this data buffer and keeps track of how many entries there are in each column and how many entries there are in each row. So after all the robots or the data from all robots has been gathered at a certain time instant, the moment in time we are going to perform triangulation on will be selected. So that moment can, for example, be this moment in time, because we have data from 3 robots at that point. So a triangulation would give great results, hopefully. So this data selection, so this time instant is selected, and the actual the OmniVision data is communicated to the rest of the algorithm. And for this, it's important to notice that these measurements can be non-chronological. So it could be that we first triangulate a measurement in the future and then maybe go back because suddenly another measurement arrives from another robot, which actually would greatly improve the accuracy. So in this case, the Kalman filter's prediction state, which is more the left part of this figure, is a little bit different than the normal Kalman filter you would imagine, because in this case it can run the model both forward and backward to like already give a prediction of the ball. So actually you could say at some point we're predicting the past, which sounds quite fun. But this all to provide the prediction to, in the end, update the state with the measurement. So from label number 3, there is the minimum distance, or the measurement actually coming. And this one is applied in the update state of the Kalman filter to the actual 3D ball position. Then also for the next slide, it's important to see that there is also a label 2 here. So this is actually the predicted position by the Kalman filter for that time instant. And this is communicated first to the minimum distance algorithm. So in code you would actually see that we're going, we have this predicted state, then here there is some minimum distance algorithms, and it's going back to label 3, where it's used in the update state of the Kalman filter. So we will now actually move to label number 2, where there are the minimum distance algorithms. So as I told you, there are like 2 kinds of minimum distance algorithms. One is the minimum distance algorithm between 2 lines of sight. So in this case we would, for example, have a robot at Rx and Ry. and they have a projection at P, Y, and Px. And we determine the minimum distance between the two lines of sight, and the midpoint of that minimum distance is actually the 3D detected ball position. This is 1, and this was already there. What the Kalman filter added is actually we could have already a prediction for the ball position. So with that line of sight, if we, for example, have only one line of sight, suppose there is a moment in time only one robot sees the ball, to get to a 3D ball position, we actually use the predicted ball position by the Kalman filter, combine that with the line of sight we have. We can determine a minimal distance there, and can also say, well, the actual ball will be somewhere in the middle, for example. Then there is, of course, aside from the Kalman filter, the data buffer, and these minimum distance algorithms, there's also a model update. This is not very interesting. It just iterates the model, the amount of time it needs to get the actual ball position, which is actually in the past, to get that one to the current moment in time. And that's the one communicated to the rest of the system. To actually see if this works, this all, we use this, I did a static test in this case to validate it and to see what kind of performance we can expect from this. So the actual algorithm is implemented on 2 robots, those 2 over there, and I've used 5 different ball positions in X and Y on the field. I will show them in a moment, and 2 different ball heights. So the one is just a normal ball lying on the ground. It's the radius of the ball, 11 centimeters, and also the green box you see over there, that exactly raises the ball up to 42 centimeters. Then for each robot, I took 200 measurements and analyzed those for mean deviation and actually the noise. If, for example, the Kalman filter would maybe not filter too good, or we'll see that in a moment. And it's also interesting to see if there's actually going to be a difference between robots, because in this case both robots communicate, and you would say that they're almost using the same information. But in this case, for example, the data from robot 1 is communicated every 1/10 of a second to robot 2. So there could be times that we actually, because the vision runs at 50 Hertz, there could be executions where we don't have that data from the other robot. Of course, the same happens on the other robots, so the algorithms will provide different results. So now the results. In this case, we see a half of the field, and we see 2 robots, one over here and one over here, marked by the crosses, for a height of 11 centimeters and a height of 42 centimeters. And at both heights, the dots represent the mean position. The mean position is the position over the averaged over the 200 measurements in that time interval. The mean position and the actual position, which are the black dots. So this is actually the algorithm working on a ball, which is just lying on the field itself. On the right, we see what happens if we actually raise the ball. So then we indeed see that there are very small differences. In this case, the dots are almost completely on each other, so it's actually difficult to show. But what we do see is that in this case, for example, there's quite a huge deviation between the actual position, the black one, and the red and the pink, in this case, position, which are the mean estimated positions of the robot. So in this case, there was actually a deviation of 36 centimeters, but on average, because the other ones are rather okay, we have an average error of 13.4 centimeters. There is not a lot of noise. It actually went down to centimeter level, 0.86 centimeters. So these are those results. So to conclude this part of the presentation, so my assignment was to research and verify whether this cooperative sensing could actually be used in this RoboCup. So a MATLAB simulation environment is used to actually identify the challenges, get a feeling for the topic, and get to some solutions. The new approach is also implemented in this simulation environment and seems to yield quite good results. The triangulation algorithm is also implemented already on the robots themselves. The static test showed that there's a reasonable accuracy of 13.42 centimeters. If I exclude the one which was like very off, so the one which had an error of 36 centimeters, then I end up with a 10.6 error, because I don't trust the measurement which was in the middle. I need to do that one again. And there are still some dynamic tests we actually want to do, because it's also quite interesting to see how this actually will perform in real time. But we didn't have time for that yet, so that will be on the roll, and I guess you will be all posted about that. Some recommendations are made in the total process. Of course, there were some points where we thought this can be better, which have not been implemented yet. For example, at this moment, and you may have also heard it in the presentation itself, the choosing which time instant is actually used in the triangulation algorithm, because this is at the moment variable, that's very easy. We just look at the maximum amount of data in the row. So the time instant with the most triangulation algorithm, triangulation data, OmniVision data, will be chosen. But this could, for example, be a much more elaborated algorithm. For example, if you consider the error covariance of the Kalman filter, you want to get that down as much as possible, because then your belief about the current ball state is best. So if we quantify the measurement error, which could, for example, be the robot to ball distance, if the ball is far away from the robot, measurement will probably be more inaccurate. Then the error covariance, I guess this one has to be determined through tuning, or we have to find some other way to determine the accuracy of this model. But combining these allows to actually predict the prediction error covariance, the P. So what I'm trying to say is, suppose we're at the moment, the Kalman filter is at TI, we could try to see if a new measurement comes in with, for example, the ball very close to the robot. That would mean that the R in this case is very low. We have a lot of belief in the measurement. Then it could be worthwhile to iterate the model backwards. Iterating the model will decrease the belief. Then applying that measurement suddenly increased the belief a lot. And then we have to iterate the model, of course, to get back to the same time instant again. What my recommendation is, you can, beforehand, you can actually already calculate whether it's worthwhile to go back, apply the measurement, and go forward again. If the measurement in this case would not be very accurate, it wouldn't make sense to, for example, go back. The current implementation of the algorithm, it sees just that there are 3 robots at this point which provided data, and those are just used because it's the maximum amount of data. But maybe it's not a good thing to do so. Then I have a slight demonstration. It's always, of course, dangerous to do something like that. Let's see. So what I will show is actually with the 2 robots over there. I'm going to move the ball at this point. Yeah, can you attach me? And this is then the base station application of Kambada, which we will put on the screen here. It's actually on that side. And then I will already turn the robot. Actually, does this go up this far? Yeah. Now we need to wait, I guess, for the robots to show up. No, that's it. Our monitors were off. So, let me. Yeah, and the other one also. Yeah. So actually now I'm going to introduce a new obstacle in the field, which will be me. And I will do it rather slowly, but in this case you should see that the ball is now lifting off the field. Oh, this is. And actually in this case you also see that there are two different balls detected. So, but they are quite close to each other. But if I now move the ball over the field, in this case so I can put it down, roll it, that works fine. And then if I lift it again, it will actually show the 3D position in the base station. So I guess that was it. Oh yeah, of course. Yeah, and then there is one slide telling. Thank you. And if there are any questions.
Of course, if there are any questions.
Is your implementation in C++?
Yeah.
Can you give it to us?
I have to discuss with Kamada for that.
Okay.
Yeah, I think this is quite an impressive piece of work for doing 2 months?
3.
3 months,
Let's
okay.
make it 3.
3 months work. And this is really, really impressive from our point of view. Walter is always welcome in our lab. Is there any questions from other people? Yeah.
Maybe I already said it, but then I missed it. Have you any idea why the error was more when you have the ball at 40 centimeters instead of on the floor?
Yeah, there are some things which are, for example, if the ball is in the air, the robot, actually the projection of the robot also increases. The distance from the robot to the actual projection also increases. So probably that will cause that bit more of error. Of course, the one I have to admit, the one in the middle is probably maybe because I positioned the ball incorrectly, that it maybe caused that 36 centimeters I was talking about. But the other ones, I think that they're actually caused by that the distance from the robot to the projection increases, and that it becomes just a little bit more sensitive to, for example, pixel changes or detections of the ball position projection.
I guess that probably there's also some influence from the fact that the blob that you get when the ball is out of the field is different from the blob that you get because of the shadow. Yeah, and the bottom part of the ball is not illuminated, so probably there will be some changes there, I imagine. Yeah.
Could also
this is
be, yeah.
just a guess.
Could also be.
Probably this will also influence that result. Any other questions? Or the invited speaker.
Selfie. It's just a quick question on the timing aspect. So you said that, of course, the delays, they cause inaccuracies, which is, of course, everybody knows. So the question is the other way around. So from the accuracy that you'd like to have, what is the requirement that you think you'd like to have from the timing point of view? So how precise would you like to know the age of your data when it arrives to you or when it becomes available to you?
How precise? In this case, that's actually also the accuracy of the timestamp in this case should be within 1/2 of a vision sample, because the data buffer, I quantize the measurements or the timestamps actually to the master clock. Maybe I can be a bit more if I have the picture. Yeah. So in this case, the measurements are stored in a grid, which is so they are quantized to the master clock. So in this case, I have the current master clock of the robot, and there is from -1/2 vision period to another vision period. I take everything together, because I cannot perform triangulation or any other minimum distance algorithm if the measurements are like slightly off time. I cannot go work on that time difference. I have to assume they are from the same time. So in this case, the accuracy of the timestamps, it would be within one vision period, preferably.
That is pretty large, right? So
yeah, in this
then
case,
you're saying that you don't really require that much precision, because then you are going to consider them at the same time, and then you're going to use them as if they were simultaneous.
Of course, yeah, so in this case, it's anyway quantized. So if I would get more precision, that would in the end give a better accuracy of the triangulation, that's for sure. But in this case, this algorithm doesn't do anything different. So it's only, for example, this could be used in the decreasing the value of the measurement error covariance, the R I presented. This could be lower if we make sure that, for example, the communication timestamps are really good, or really accurate, sorry.
More serious. Oh my God. Just one point. Currently, we are not synchronizing the clocks between the robots, which is something that we want to do. Okay, but currently we are not.
How can you deal with false positives? So let's say one robot detects a false positive ball somewhere outside the field.
Yeah, at this point, that's actually, in this case, out of my scope, out of my assignment. I get the ball position or the ball projection actually from the vision system, and I assume that they have taken care of false positives in this case. So, really easy. So no, so in this case.
We don't have anything in this area currently, so we need something because we have moved from C#.
Okay. All right.
Maybe to elaborate.
No, but that's of course an important question and a serious question, of course, how to deal with that particular situations.
Maybe a little bit more elaboration on this. So, what was it again? So actually, the ball position it has already the vision module detects a ball, and this one is when it goes through the integrator here in the Kambada robot, and that one already determines whether there, for example, there is a false positive, and filters out those, and then I am left with only one ball position, X, Y, and that's where actually this algorithm comes in and starts working.
Basically, it comes down to the resilience of the work that is before his work,
yeah.
Right?
Which
depending on the capacity of taking out false positives.
Yeah.
Maybe you could do something to at least see something strange.
Strange, right.
The closest distance between both trajectories is too far away from each other.
Something that we'll probably discuss tomorrow, that you have proposed maybe 1 or 2 years ago, that was to discuss level of confidence of what we get from our vision systems, for instance. I guess. Let's see. Other questions?
Okay, I'll be fast because I think we are a little bit late. So I have to reuse the words from my colleague Bernardo. I think you did a very nice job for the small amount of time. So congratulations for that. I think we have here interesting results that, of course, we will share to everyone, not only the present, but everyone in middle size. The question is to maintain a half pass really fast. You have interesting results. Of course, it's missing the final part of trying this with the robots and the ball moving. The question is, did you start from the same position in the beginning? At this point, if you have to recalculate your tasks, do you start from where you started before? There was anything that you would like to change regarding your approach?
In like the more like on the process side of, or the more the design of the algorithm?
I was thinking more in design of the algorithm. After what you saw, do you think there was anything different that you would like to try in the beginning?
No, actually there is not. Maybe indeed at the clock synchronization, that was something we were scared about at first. Maybe we could have picked that up at the earlier stage to like already implement that to increase the accuracy, because at this moment indeed the clocks are not synchronized, or we don't know actually. So, but actually the rest of the algorithm, I think it would end up the same. Yeah.
Thank you very much once again and congratulations.
Yeah, thank you.
Thank you again,
Now I am. Right. Thank you. So my presentation will be the not last one, because after me there is invited speaker, self-invited speaker, right? No, it's a friend of us, actually, and most of you probably know him, but I'll give him the words in a few minutes. I'll try to go fast through my presentation. Actually, it has not anything to do with Cambada specifically. It has to do with middle-sized league, and something that we have proposed last year to the RoboCup Federation for some funding. So this work has been partially funded by the RoboCup Federation, and and basically why I'm presenting this this afternoon is because we are hoping that tomorrow we can use this tool and start moving on in order to take some advantage of it, namely during the next competitions. So basically, this is basically the summary of what I'm going to show. The motivation was that, as you know, rules basically change every year, sometimes a bit, sometimes a lot. It depends on the challenges at the moment. We have been using a referee box that has been stable for a lot of years now, but that in some aspects has not evolved together with the rules. And at a certain point, we felt that it would be important that the ref box could include the new possibilities and the new targets that we're aiming at this point in the roadmap of the middle-sized league. Need, for instance, for inter-team cooperation is one of the needs that's been emerging. Last year, we have done a very interesting work in Eindhoven during the hands-on day, putting a lot of teams sharing their world state vision and showing that world state in different base stations. Also, we'd like to have requirements for better debugging tools, information that we can get from both of the teams that are playing at the end, let's say, not during the game. During the game here means that you are acquiring information during the game and then you can actually provide that information afterwards for debugging or for benchmarking. More realistic information for the audience. I think that that's one of the problems of the league. We have not only to explain what is going on, but to have to also provide some information for the audience to see what the robots see. So we can explain what is happening, but it's harder for the audience to understand what the robots can actually perceive around them. More effective benchmarking tools, I think they are more and more important over the time. Also, taking all these basic motivation that I have presented, the objectives that we have proposed was to create a new platform-independent application, a Refbox basically, written in Java. This has nothing to do against C++ or whatever. It's basically to be platform-independent, and the trustees last year appreciated that, I guess. Support for fast action modes with interlock capabilities. This means that we want to prevent as much as possible human errors actuating upon the Refbox. Extension of the currently used protocol. This actually makes sound a little bit strange because we only implemented the old protocol and not the XML version, but it's rather easy to implement also the XML, but extension in the sense that we want to introduce other types of information to provide to the base stations and also to get from the base stations. Extensive log data, not only from the game itself, but also from the teams. Easy configuration as much as possible. Remote audience and field referee data show. Ready for voice interface for human coaching. That is something that is already on the rules, but it's not been possible until now because there is no support for that. A gathering of both teams world model and fully configurable and open source in the sense that all the community can work upon this and develop new solutions. In terms of the basic architecture that has been proposed and has been evolving, so this is not static in the current sense, let me see. Yeah, okay. Basically, what we have is a central state machine together with a control graphical interface. This is what the current Refbox uses together with the communication model, which is wired to both teams' base stations. So this is the current solution. What we wanted to add is to have the possibility of having clients to this central machine, to the Refbox, that can either present the information it has upon the game and upon information from the teams in different formats and different visualization modes, and also clients that can provide input either to the teams or to the Refbox itself through different means. For instance, using voice or using any kind of device. Probably some of you remember the device I presented 2 years ago for the referee. Okay, now we have that integrated into this Refbox. Okay, all the information is to be stored, and then the idea is also somewhere in the future, not now, to have the possibility to input ground truth data to the system, so that we can actually have some form of benchmarking regarding the results we get from our team and from the opponent team. So if you now look into what is the base of this new Refbox, please do not be too critical regarding the graphical aspects. Okay, this is not the main point. You can suggest anything you want regarding that aspect, and you can change it. But the idea was to divide the area. It's a little bit dark, but never worry. Divide this in several areas, which are quite distinct from each other, so that the number of mistakes from human errors from the referee, the Refbox referee will do when acting upon this situation. So this is a pre-game situation. This is the time elapsed. Now we'll have here also the actual game time. Means that the referee has not only the running time, but actually the play-on time. And this is an extra information for evaluating the performance of the teams during the game. And this is also a tip for the referee for how long it should extend the halves of the game, for instance. Okay. Don't be shocked with the next image. It's a little bit colorful. It's on purpose, let's say. And basically, so on top you have the team names. Now with this ref box, basically when you connect to the ref box, it automatically pops up your name because it has the list. The IP addresses are assigned to the teams, which means that it's possible to input directly the name of the teams and present them there. At the center you have information about the current game status, current score, game time. This is the actual played game, let's say. On the left and right side are those commands which are somehow commands and information which are related to each of the teams. So basically these are the commands for each time of free kicks, kickoffs, free kicks, goal kicks, throw-ins, corners, penalties. Also for the goals, repairs, and yellow and red cards. The red card hopefully is never to be used, but you never know. But as you probably have noticed, we have been pushing towards being more proactive, showing the yellow cards. And so the possibility of actually having at least double yellow cards is now much more common. In the bottom, you have some miscellaneous information, event history, and some team counters, which is basically something just to check if everything has been going okay. And now you just forget about, with the new rules, just forget about robot numbers. You know that a team can have 5 robots, so these circles will represent your team. It doesn't matter if this is the goalkeeper of that one. So there is no relation between the numbers and the robots. So just to show in a very fast way, this would be a situation for, this is pre-game still, so this will be a kickoff for Team A. The start is ready to be pressed. You can always press stops. So stop is always active by default, which means that you can always stop whenever you want. The reset will reset the base station, the ref box. This is a normal play-on situation. In play-on situation, the only thing you can do is stop the game. Nothing else can be done. This is a situation where you have indication that you are in the first half, you are in the stop game position. You have, this is actually not, I don't like this, we are going to change this. This is a 1, not a 7. 1:29, the actually played time would be 1:14 seconds, okay? In the center, you can have the common commands, which are drop ball, park. Of course, you can only have park after ending each half or the game, end part, and on the sides, you have the types of restart that you can use, also the yellow and red cards, the goals. Any problem? No. Okay. So this is an example where, for instance, the team A, cyan, will have a yellow. Okay, so this is, notice there, this is the first yellow card, not the second one. And the second team, Team Magenta, has a player that is being taken out for repair. So the timer is over there. And as I'll show you afterwards, it is also available for the main referee. And basically, if you take another one before this one reaches 0, both of them will start by 30 seconds again. A thing that is slightly different, of course, you can change that if you want. I am no longer with the execs, but if you want, it's not clear in the rules if this time is actually counting during the stoppage time or not. Okay. So it's something that you can decide. You know, it changed. Okay. In this situation, for instance, you still have one player out for repair, and this unfortunate guy had got the second yellow, and now he's 98 seconds away for getting into the game, and knowing that these 98 seconds does not include half times, so it stopped during half time. Okay. Another thing that was not supported by previous refbox is overtime. Now, after ending the second half, you can choose for a kickoff, and if you select a kickoff, you enter in overtime. And now you have a first and second half overtime. That will normally be more 5 minutes. Okay, so when you come to the semifinals and finals, and you get in this situation, it would be a draw, 2-2. Then you can have an overtime. And after that, if it's still a draw, you went into penalty mode. Okay, so This is all integrated into this solution. One of the things here with this is based on the old protocol, as I said, but we also introduced a new command for asking teams for this current world state. So it is requested on a periodic basis. This is based on the document which has been produced, and the interface is based on a JSON structure. And one of the things that we'd like to invite you tomorrow is to discuss the structure, what you'd like to put there. Of course, it's not fixed in the sense you can add up some extra information if you want, but at least there is a minimum amount of information that should be there. This information is then relayed to local storage and to the audience data show. Also, the information regarding all the states of the game is stored, which means that after the game, this information is deployed to both teams, and you get an historic view of everything that went on through the game, not only from your point of view, but also from the point of view of the other teams. Okay, sorry. Relating to the audience data show graphical interface and also to the referee box, since this is based on the concept of producer-consumer solution, basically. This will be a client of the ref box, and will receive the information regarding the game and information from the teams. So one possible view, which is implemented and we can test tomorrow, of the audience data show would be something like this. Okay, it's not necessarily this, but it actually is working. The teams can also provide the form of their robots if they want in an XML file. No, Jason? OBJ, okay. OBJ form, which means that you can have your robots designed and put it into this solution. There is something that we have been discussing about using only 3 letters for each team. I don't like the solution, but somehow this is based on the standard that we see on FIFA games, right? So, huh? Pro Evolution Soccer, okay. Pro Evolution Soccer. Result, time of game, and what the teams say that they are seeing at that moment, okay? We, at this point, decided, and it's something that's open for discussion, that we should not show the obstacles that each team sees to the audience, because it would be too confused. And we also have to decide that maybe we'll be showing 2 balls, 1 for each team, but you have to decide what is, if you have more than one possible solution for the ball, what is the one that you want to show. Okay, this is open for discussion. Of course, you can also show the audience what is, for instance, if there is a kickoff gambada, this will appear as a, how do you call it? Sliding animation. Yes, a sliding animation, okay? Kickoff gambada, and goes down again, and then the robots will move, okay? And there will be a whistle and the game on, basically. Okay. Yeah, right. Okay. For instance, again, this is not necessarily the outcome, but if you have this this display on near the ref box and looking towards the field, the referee can have all the important information delivered to him. Okay, so we know that the game time is 1:34, effective time is 36 seconds. The current status is first half, last command send was stop, it's here. And the status of team A will be the name of the team, of course. Robot 4 is double yellow and still 97 seconds to go. So those situations that you see today, that is the team leaders asking, referee, can I put number 3 in? He says, I don't know, okay, just wait another moment. Now you can actually check it here. R0 is out for repair and still waiting. You still have to wait 18 seconds. When it goes to 0, okay, you can let it in. Okay, those situations hopefully will go away, basically. So regarding future work, and some of it is already being tested, we have already started testing a solution for voice interface for human coaching according to the rules, which means that we will hopefully have 2 microphones using the left and right side of a stereo connection being sampled and sent to the base stations during stoppage time. And for this, we'll use a different IP address for not getting confused, confusing this data with the data from the ref box. And if it's up to the team to use or not to use the voice interface for human coaching, and this will only be delivered during stoppage time. During game on or during the restart, it will be blocked. Also, the possibility, if someone's want to work on it, for a voice interface for the main referee, which would be nice if you want to train how do you call it? Speech recognition, right? Speech recognition software that can be understood by Chinese, Japanese, German, Netherlands, people from Portugal, for instance, Spain, Brazil, whatever. It has to be able to understand, but I think that also the dictionary is rather short. So basically what you want to say is start, stop, and maybe the kickoff, goal kick, and the name of magenta and cyan. So I think it's not impossible to do, and it would be nice to basically removing the ref box assistant and having the main referee doing all the tasks. Okay. This is something also for the future. It would be also nice. I already submitted a proposal 2 years ago for developing a system like this, but it was not funded. At the point or at the moment, they thought it would not be interesting. I think it would be interesting in the future if you actually want to have some sort of benchmarking, good benchmarking in MSL. Okay, so basically that's it. Tomorrow we'll have a chance to play with this, do some work around it, and we'll see how things go. That's something to discuss tomorrow. And after that, I'd like to, for our next and last talk, I'd like to invite, I don't know if there is any questions, but I think we can keep the questions for tomorrow, right, about what I said. And I'd like to invite Professor Luís Almeida from University of Porto. Luís, queres passar a apresentação para aqui? Não. É por causa do streaming. A gente sabe fazer.
Yeah. All right. Good. So let me just start by telling you the story. Is that I mean, we were discussing about other issues, and then he said, "Well, I'm so busy because next week I'm going to have this middle-sized league workshop." Then I said, "Wow, that's cool. So don't you need anyone to say something about communications?" And I said, "Yeah, we actually have this slot. So good." So that's why I'm a self-invited. So you know, so the idea is actually also this year in FA. So when we were discussing about next year, and Gerhard was doing this presentation for Germany, right? Then I was there at some point, and they said, "Well, if there are any communication problems, that's with Luís." And I was so embarrassed because I'm actually the last person that you should call if you actually have one of these serious problems that you need a hacker to, because I'm not really a hacker. So I confess myself. Okay, so the thing is, I was, you know, just involved in this work for communications for teams of robots, more at the protocol design level, and thinking about what kind of properties would you like to have in the communications for supporting these collaborative behaviors for teams of robots. So that has been my work already for several years, and I had a couple of students working on this. So one of them actually came up in the scope of the Combater team. He came up with this software that I will just briefly explain you later on. I mean, I think probably some of you know about it, and maybe you haven't even used it. Okay, so I will just, I also confess that I didn't have time to prepare a very nice, presentation, and I also thought that at this time you were not really expecting any kind of presentation, so I will do something, fast and something interactive. So I would like that you interrupt me at any time if you have any doubts and if you want to say something, because otherwise you're going to fall asleep, and I would fall asleep as well, and it would be very uncomfortable to fall asleep in front of you guys. So, I mean, some of these slides are generic, but I mean, I will jump into MSL quickly. So, what for these teams of collaborating autonomizations? I don't really need to tell you much about this. You know, from robust and wider sensing to cooperative sensing and control, so efficient actuation. So there are many different reasons why we should use teams. Of course, then collaboration requires communication, because sometimes it's not really explicit communication. It can be implicit communication, but some sort of communication needs to be there. Otherwise, we don't have effective collaboration, right? So it can be from these warehouses that are now a hype with this Amazon stuff and all these things, right? It can be surveillance, it can be transport or rescue, or it can be MSL. In any of these cases, we have communication, right? And what for is the communication? So there are several reasons why we want to communicate among the, the agents. So one of them is sharing state and sensing, right? And in this case, if we look at the characteristics of this kind of communication, is typically short, medium-sized data and typically regular. So it can be periodic or quasi-periodic, something like this. But we also have to communicate events. So something that happens, we want to say, for example, in this case of MSL, we want to stop the robots because the referee says stop. And they should stop. And this is, of course, we can convert event to state, and we can have, this information transmitted regularly, but it's nicer if we just send events. And this is typically a periodic short data, but it has a specific requirement on, it has a specific requirement on reliability. As opposed to the previous one, if a given message doesn't arrive, we can wait for the next update, and the state is regularly updated. And the second one is just transmitted, from time to time. And if we miss it, then it's a mess, right? So it should be transmitted with some reliability in mind. And then, of course, there are other kinds of communication, like, for example, streaming multimedia, which is important in some applications. For example, in search and rescue, it's very important that the robots can establish a multimedia link with, the front robot in case it detects someone, for example, a person, right? Establishing audio in particular is extremely important. But also video is also important in many of those cases. All right, so we are going to focus in this one because it's the one that uses the, the medium more often, right? And the other thing is that because we are talking about mobile robots, the communication has to be wireless. And when I say wireless, of course, we all say, oh, wireless Wi-Fi, or radio frequency. Not necessarily. It can be audio, right? Or it can be, vision. So it can be any of these things, and this would be cool, I know, to have, new ways of communication, with the robots doing some kind of maneuvers or lighting up lights or doing something in order to communicate in other ways than just radio frequency. But of course, radio frequency is so convenient that we will use it for many years, I think. All right, just a few things about the wireless. You probably know about it, so I will not just, I will not spend much about this. You know that it has these bands, and you know that it has several channels, but the channels are limited. Some of them are actually overlapping, and so we have interference if the channels are overlapping, and within the same channel, of course, we have interference if the transmissions overlap in time, right? So if they are at the same time, we have interference across the transmissions. When we look at the topologies, there are typically two kinds. The infrastructure, which is based on access points, is the one we use, all the time. The nodes have to register in the access point, and then they communicate through the access point. So all the communication goes up to the access point, down from the access point to the nodes. It's interesting that some of you may not even be aware of this, but for example, when we send a broadcast, or it's not a physical broadcast because it's always physical broadcast in this case, but for example, when we send a logical broadcast, it's with access points, it's only broadcast from the access point down. When we communicate up to the access point, it's always unicast, so it's one-to-one communication acknowledged, right? Okay, which is more reliable in that, from that point of view. But of course, we can also have ad hoc, which is much better when we have a large area and we may want to explore this kind of flexible layout, right? Like, for example, when we have search and rescue cases, I think this is much more adequate than okay, a star. But in our case, MSL is a star, right? That's what we use because it actually facilitates, and that we are going to take advantage of that. So I'm just going to tell you later on. This is a little bit about the contention resolution mechanism. We call it the arbitration mechanism. So how does it work? The basic mechanism, we call it CSMA, with collision avoidance. This is stands for carrier sense multiple access. So it's basically one of those protocols in which before you transmit, you listen. And if there's silence, then you go, right? If there's something going on, you wait, right? Or you do something else. Either you back off or you wait until it's free. In this case, it's what we call a persistent protocol because it waits until the medium is free. Once the medium is free, then it computes a random interval, and after this random interval, it tries to communicate again. Right? If there is communication within this random interval, it stops counting time. When the medium becomes free again, it continues counting the interval. So you see that case, there's station A transmitting. There are two requests, B and C. Because they detect the medium busy, they defer their transmissions. When the station A, when it ends after a certain interval called this, which is not relevant now, they compute random intervals, which are basically those, you see green, B, you see green and a bit red, and then you see green on station B. So the interval of C is actually shorter than that of B, and so after that interval of synchronization, when station A ends, then they basically start, I can move, yes, I'm wireless, okay. So they start here counting their random interval. And so you see this interval is shorter than this interval, so this one starts first. It wins arbitration. When this one detects this transmission, it stops counting time. So this little bit of time is actually postponed to after the end of this one. So when this ends, then this one counts this little bit of time, and then it starts going. Now, you can see that we may have another request here, another request there, and they are all trying to access at the same time. And this just leads to a phenomenon called thrashing, which is the fact that if we have a lot of communication requests, the medium is really busy. It happens that we have a lot of contention here, and these random intervals are not enough to separate all the requests. And so the probability of collision is very high. And when the probability of collision is very high, then this jumps, because if there is a collision, then they do a back-off, which means that they jump, they wait for a certain random interval of time, and then they come back later on, which really creates long delays, and at a certain point in time, you actually lose the packets, because there are only 16 retransmissions at most, and then it's gone. All right, a few observations. So is it okay until now, or you know all this, right? Okay. Yeah. The contention window is exactly the size of the random intervals that each station can pick. So they will pick one interval within this size, right? That's why it was there. It was not clear. Sorry. Yeah. So they can pick, it can be this small or it can be this large. It's actually 1 over 32 of these. But I like to touch. I'm sorry. I have this thing, yeah, and I love the screens where I can, reach. But of course, I can't reach the upper part. But well. All right. So, few observations. Basically, this is a shared medium, right? So it's like, look at here. We understand each other. Why? Because we are talking, one at a time, right? Now we can try to talk everyone at the same time, right? You know the consequence. The consequence is that we are not going to understand each other. It's basically the same, right? Now, if we are just a few, now I can detect when you start talking and I stop, right? And sometimes we have this interesting thing that we start at the same time, we stop at the same time, and then it takes like a few seconds until we actually, you know, keep it going. But I mean, we are kind of smart. We have these random intervals, and we detect very small differences. And at a certain point, one of us, you know, starts talking before the other, and the other waits, right? But this can happen, right? So it's very important to know that when we have a shared medium, there is no other way that we can communicate unless we serialize communications, right? That's the thing. Unless we do what we call frequency multiplexing, which means multiple channels in parallel. But we are limited in that point as well, so we don't have channels for everybody. And so we have at some point to use the same channel. Now, abuse of this communication leads to degradation of communications. That's basically what I was telling you before. And under high traffic, it's very nice to have, or very important to have access rules. I will tell you a little bit what is TDMA. TDMA stands for time division multiple access, which basically means that we divide in time and we give slots to different robots so that each one talks in its own turn, right? And so this way there are no more collisions, right? Improve effectiveness of channel use. So if we do this, if we create a rule so that we talk one at a time, we don't need to do this arbitration, right? And so it's very fast. We can really reach a high utilization level in the shared medium, right? So it's very effective. But it's very interesting as well to see that sometimes we have periodic interference patterns that cause degradation even with light loads. And this is very interesting to understand why. And this is, I think, very common in scenarios where the robots actually have to share state to collaborate. So imagine that we have some robots sharing state with a given period, and other ones with a period that is, you know, kind of similar but not exactly the same. And so the phases will rotate, and that there's a certain window in time in which they will actually transmit or start transmitting in very short separation, and so there will be a high potential of collision. It's not necessarily that there will be collisions every time, but we may have a high probability of collision during a certain interval. Then they get out of phase, and then they will be okay for half hour. And then after half hour, we have 2 minutes or maybe 1 minute of very bad communication channel. And then again, half hour okay. And then again. So this is also pretty much undesired. So these are the things that we have. Now, I'm taking too long. So I would like anyway to jump to another presentation that I have, which is an old presentation from 2008 with logs from RoboCup 2008 in Suzhou in China, actually made by Cambada. So they were made by Federico, so there was a student that was working on this at the time. So we did a few logs, right? And these are the interpacket delays that we measured from the different teams. So how frequently were the teams transmitting? This is basically what it means. It's a histogram of the time differences between consecutive packets of the same team. And it's very interesting to see that we have a wide variety of situations. And whenever we have a close concentration towards zero, this means bursts. So teams that are sending a lot of information in very short periods of time. And bursts is, of course, the worst thing you can do in terms of sharing, you know, with a fair kind of way, right? Because when you send bursts, you create a high potential for interference, and the other ones that want to share the channel will probably have a very low probability of doing it successfully. So these two teams in particular were basically preventing the other ones to transmit effectively, right? You see the other ones, the bars on zero are not so high, and they are more spread out in some sense, which means that they have transmissions that are more separated in time. All right. Also, when you look at the size of the packets, it's very interesting to see that some teams use, you know, moderate packet sizes. Of course, packet sizes means time of consecutive use of the channel, right? So long packet sizes, long interference. Short packet sizes, short interference, and you give everybody, you know, the chance to transmit more closely together. So that team over there was, together with this, the two ones creating the least interference, or doing what we call a parsimonious use of the channel, right? So using the channel to send only small bits of information.
This one was also okay, although from time to time there were, large, maybe state messages. I don't know what they were transmitting. That one was also fine. When we look at these two, I mean, these were probably sending raw video, something like this, right? So this is a very nice way to block effective communication, right? So, I mean, if you can't win in another way, then you can try this way. But of course, it's not a very nice way, right? So we have to do something about this. These were numbers. So wide variability of packet sizes, long bursts. All right, so in some cases, of course, at the time, some people were still using B. Of course, nowadays, I think everybody uses A. And, but with B, there will be a strong overload of the medium. I mean, it would be impossible to transmit that amount of information in B. Very short interpacket intervals. Okay, all right, so all that. So problems that we detected regularly with the Wi-Fi thing. Infrastructure configuration, so regular wireless internet access in the venue created, interference with the games. This is sometimes happening. Team communications configuration, because there were typically teams that were not really aware about how communications work and had very strange and weird configurations of their interfaces that would create tremendous interference with bursts as well. Lack of policing, this is typically a problem because if you don't police, you don't know what's going on, right? So if you don't know what's going on, I mean, the teams cannot communicate, and then they think they're doing something wrong, and then the games are not really nice, and it's really a pity. So, and also then the channel overused by teams, which is a problem, right? So, okay, misconceptions. I think this is also an interesting slide. This is what we typically hear, right, about communication. So no need for restricting Teams transmissions, but unfortunately the bandwidth is limited. So, I mean, if we have a team abusing, then there's nothing, remaining for the others. So larger bandwidth solves the problem. It's always nice when we have this step in technology. When we were using B and we started using A, oh, it's a highway. We can send everything. Big bandwidth, right? Wait, it's just a couple of years and everybody will be using everything they have, right? And so we are back to the same problem. Every time we have more resources, we will come to the point soon after we start using those, and we are going to use everything that we have. It's always the same. So use technology with QoS support. This is very nice, but how can we differentiate the teams, right? So the team that pays more, if you pay more, you get a higher quality of service class. It's also a good possibility, right? No need for technical verifications. I mean, we've seen the problem already. It's also interesting to see there was this year, there was a chance of presenting an invited paper on the developments in RoboCup. I don't know exactly where, but it was Peter Stone that was doing it. And he prepared this 2-page abstract on developments, recent developments. And it was really cool. I mean, you could see in just 2 pages many different developments in RoboCup in all the leagues. It was really cool. One of them just caught my attention. Audio communication in SPL. Wow, great. And then it said, one of the teams just tried using high-pitch frequencies that you can't hear, basically ultrasound, in order to do communication across robots. And it was perfect. Of course, there was no one else using that. Cool. Now, the thing they were doing, okay, now we are considering using this for everybody. Cool, cool. All right, let them do that. I mean, no, I can tell you, it's of course good to diversify. It's really good to diversify, but it's always the same. If the medium is shared, there is no way out. We need to coordinate. Otherwise, there will always be a mess, right? This is the main thing. Okay, so let me go back to the other presentation and show you a little bit more about the things that we've done, and some of you probably used already. So our focus is on sharing state in periods of high team interaction. So we would like to do low overhead, so somehow keeping communications and computations under control, so not exaggerating on the amount of overhead we are imposing, improve data timeliness, and allow a quick access to data, and
age information. And I enjoyed really your presentation when you referred the importance of age. It has been one of the drivers when we developed this protocol. So we wanted also to separate data access from data transmission. These are two very important aspects. So when you are executing a process that needs remote data, if you request the data at the time that you are executing, you halt your process, you ask for the data. When the data comes, you continue. And this means that all the delay of communication is inserted into the processing latency of your cyclic activity or whatever, right, your process. So this is something we wanted to separate. So one thing is computations. So you have your processes going around, and they are not at all influenced by the latencies of communication, completely separated. And then you have the communications on the other side, and the communications, what are they doing? They are just making sure that you have local copies of the remote data that you need, so that when your local processes need remote data, they just use the local copies. So this is the separation that we wanted to do. Okay, and of course the case study was MSL. So a couple of contributions that we did. So this that we call the real-time database. It's a simple shared memory kind of middleware. So I will explain you a little bit about it. It just uses read-write semantics. It's very simple. And it also gives us temporal decoupling between application execution and communication, which is exactly what I was telling you before. And it provides you age information on the data, which is something that we also wanted to give. So this is what we call data access. Then we have reconfigurable and adaptive TMA protocol is a way of organizing the communications in a shared medium. So this is the way that we coordinate transmissions in a team. It's a protocol that is self-synchronized, which means that it does not require clock synchronization. It just synchronizes on the transmissions and receptions. Team broadcast dissemination, so all the data is broadcast among the team, or multicast in this case. And it copes with external traffic. This was very important. So it's done in a way that even if you have other traffic going on, and if it sometimes interferes with your traffic, your protocol still works, right? Because there are protocols that if you mess up with the nice rules that they have, they will just break down. And it's not the case, right? So it kind of tolerates. So this is what we call data dissemination. So data access, data dissemination. And this has been, this code has been available. It was on Google Code, but then Google Code had just been frozen. So the code is still there, but it's frozen. And we moved it to Bitbucket, and so it's still there within this RTDB. All right, so a little bit, these are not many slides because otherwise you would be dead, but I think that some of you already know something about this. So this is just to give you an idea about the main topics. So we have several robots. In each of the robots we have this database. And this database is actually a representation of the world state. And it has two parts. One part that is local, and another part that is a representation of the data shared among all the robots. And this part that is shared is actually organized into a set of structures in which each structure represents the data shared by one robot, right? So in this particular case, we have over there the shared part with 3 agents, 0, 1, and 2, and the local part. And you see this in boldface. On agent 0, it's in boldface because it's its own part. It's where it writes its data that appears automatically or magically in the other robots, right? Robot 1 and 2, then they see the data from agent 0 there. They read it from there, right? Agent 1 writes its own data in the structure agent 1, and then it appears magically on the other 2, and then the same for agent 2, right? So basically the interesting thing is that then all the processes, motion, vision, odometry, control, whatever you do, it's all using local data. This data can be real local, or it can be a local copy of remote data, but it's all local, right? This means that you do not include any communication delay in your processes. That's the thing that we wanted to do, right? Okay, but of course, then you
then you could ask, oh, then it's perfect. There's no communication latency. Wow, we sorted out. No, of course, it's impossible. You know that communication takes time by the laws of physics, right? And so the thing is that we are just decoupling and putting it elsewhere. So it's like the cap, and then you have the carpet, and you put the garbage under the carpet. So we put the garbage, which is the delays of communication, under the carpet, and we have nice process behavior in terms of time. But of course, the communication delay is there. And you notice it when you actually do applications. Why? Because when you consume the data, it's local, but the data itself has a certain age. And as you said very well, so sometimes it is old. And so if it is old, then your process, at the end, the outcome of the application will be, you know, inaccurate. There's no way that, well, I mean, there are ways to go around it, but it's inevitable anyway. All right, so I already explained how this goes. So 0 shares its data, then 1 shares its data, then 2 shares its data, and that's it. That's the paper where we share this. All right, so the communication stack, we have the database with its local variables. We have the shared variables, which are the variables that are going to be written and sent to the others. So it's from the local perspective what I share with the others, right? And then you have the remote variables, which are the variables that the others shared with me. And so I receive the variables from the others, right? So I have two very simple functions to access the data. It's just get and put. So put allows me to write in the shared variables. Get allows me to get data from the remote variables. And then on top of this, I have all the applications, right? Then this goes on top of this reconfigurable and adaptive TDMA protocol, but it could go on top of other protocols. They are actually decoupled, these two layers, right? And then we have this working on top of UDP-IP, but it could also be directly in raw sockets, but UDP is more flexible to use and gives us this interesting part. So this goes then into the wireless communication. And of course, we have the wireless medium, and we have all the robots with a similar stack. And then the reconfigurable and adaptive TDMA synchronizes all the copies of the real-time database. That's basically what it does, right? So it keeps all the remote copies updated, right? All right, so a little bit about age. So what we did about age is that there's actually a parameter together with together with each item inside the database. There's the data, actual data, and there's the age of the data. And so how do we compute the age? So whenever it's written with the in the producer side, we write something into the local RTDB, and locally a timestamp is taken. Then when the protocol comes and takes this data item, right, this datum, to send it to the other side, then another timestamp is taken, which is T2. And then we actually subtract T2 from T1, which is the age inside the producer side, and we put it inside the message, and it's going together with the data itself, right? And so when it comes to the receiver side, then another timestamp is taken, which is T3, and then we do an interesting thing, because we subtract the age in the producer from T3, and we save that in this field. And then when the consumer actually reads the data, there's another timestamp taken, and then we do at the time that timestamp T4 minus whatever is already saved, which is minus T3 minus T2 minus T1, which basically means at the end it means that we do H equal T4 minus T3 plus T2 minus T1 plus an estimate of the wireless communication delay, right? So this estimate is a little bit fuzzy. It depends on how well, I mean, so the communications are nicely separated, then the delay is typically, let's say, short, and not so, the jitter is relatively small. Now, if there's a lot of communication, the medium is really busy, then we will have a jitter there, and so the estimation of that part will be a little better, a little worse, sorry. Okay, so you see data, we put it in the RTDB. When we do get, we extract the data and the age automatically. All right, so a little bit about the protocol. So it's, as I told you, 1 slot per node. It's kind of a reservation, so we reserve 1 slot per node. There's a dynamic reference election, and this is an interesting thing, because when we have a round, you have to know where the round starts. So where does the round start? Is there, there, there. We did a version in which there was no start of the round. So it was like a window that was constantly moving. But then it could create some fuzzy and phenomena or artifacts. And then we could even have the team converging to different values. And so we just came to the conclusion that we still have to do that, and we sorted those problems in a different way in an ad hoc version of the protocol. But here we decided to just use this way of creating one reference, which is the one robot that has the lowest ID at the moment, and that will be the reference. So it's a dynamic reference, and the others synchronized to him, right? So we will see that how that works. So we have, in that case, the reference, they have all these dynamic addresses that always start with 0. So 0 is the reference, and then 1, 2, 3, 0, 1, 2, 3. And then what we actually do is that the transmission of 1 is TX win after transmission of 0. And 2 is 2 times transmission. And 3 is 3 times, right? So this has the benefit of maximizing the separation between the team transmissions, which accommodates basically interference that there is in the medium. Now, if we have strong interference, we may have these delays. Our transmissions can be delayed. And if our transmissions are delayed, then what we do is that this interesting feature of actually delaying our next transmission. When we delay our next transmission, this is like a phase rotation of your round. And this is also interesting because if we have one of those periodic interfering patterns that would cause, a critical period of constant, collisions or high potential collisions, with this way you shift to the side and then you get rid of this effect. And this is actually very interesting and very effective for that purpose. All right. Okay, around phase rotation. This is how we compute the phase. One interesting thing is that only the node 0 actually compensates the delays, right? So the other ones, they just use offset with respect to the reception of node 0, right? So this was very important to allow a quick synchronization of the team and resynchronization. This is just to show you how effective it is. This was just one particular case, exactly in the same situation in which we used this adaptation, and other cases in which we were not using that adaptation. And so we had a round of 100 milliseconds. Whenever we have one of these jumps, is one packet that was lost. And so with this kind of synchronization, without it we have many, with we have much less, and then sometimes without we even had 2 consecutive packets lost, even 3 consecutive packets lost, and those cases were basically eliminated. And if we look at the distribution of delays, when we have our synchronization in place, you see that even with interference, but it's a periodic interference with pings that we are created here and with actually even high load, you see that the jitter is relatively contained, right? And so we have here a high peak in relatively low delay. And of course, in cases in which we don't have the synchronization, and sometimes we have critical periods, we actually created a critical period so that we could see what could happen in that case. We have a much larger, so about something like about 3 times the jitter, and the average is also like 3 times larger, 4 times larger, right? So there's a strong impact in reducing delay and making your transmissions behave better, right? So if you, this I will skip, but this is just to say this was a relative localization that we were doing, and even at the application level, so look at the result of your localization with and without, and you see that the localization is really bad without the synchronization because of all the delays, right? The accuracy is much worse, right? Because the delays are all messy, and the behavior of the channel is not good, and it really improves the performance of the application just by improving the communications, just by improving the quality of the channel. All right, so the final thing to show is that we have these 2 dimensions. So one is, okay, we create this round. We have 1 slot per robot. Nice, okay, but if we did it just like that, then you know perfectly well how dynamic the teams are, right? So sometimes you have one robot, other times you have two, then you have 5, then you have 4, and 3. So if you kept this, if you include the base station here, let's say you had 7 slots. If you keep 7 slots all the time, then sometimes slots are unused, right? Because the robots are off. And this means that the transmissions would be closer to each other, which means more sensitive to interference than needed. They could be more separated. So this was the motivation to do this kind of reconfiguration of the round. So we keep the same round, but if we have 2 robots, we divide it in 2. If we have 3 robots, then we divide it in 3. If we have 4, we divide in 4. And this is always constantly being adjusted to the current membership, which means the current composition of the team, right? It's constantly changing. We still do the adaptation. It's exactly the same. So one interesting point is that we keep the round. We don't change the round, because there were other approaches in the past in which the slots were added. The slots always had the same size, and we added more slots or less slots to the round, which basically meant a shorter or larger round. And this is bad. Why? Because the applications actually they work on top of this round, right? And because this round is how fast your data is refreshed, right? So if you change it, then you are always changing the properties of the timeliness of the timeliness properties of the data, right? So if you keep the round the same, the applications don't feel any difference. If you have 2 robots, 3 robots, 10 robots, or 5, it's the same, right? So this is the reason why we really wanted to keep the round the same. And this, of course, really provides this maximal separation between the teams with any kind of composition. This is actually a plot from a play, a log from MSL play. So you have here, this is actually the node 0, node 1, 2, 3, 4, and 5. The last line is the next transmission of this one. So it gives you an idea about the round size, right? So you see that the round is always the same, around 100 milliseconds, but then it is adjusted. You see those spikes? These are adjustments because of the delays that the other nodes suffer. Now, you see here is the actual membership. So we have 6 nodes. At this point, you see over there that this is 1, 2, 3. 3 actually, no, actually it's the red one that entered. The red one entered there, you see over there. And when the red entered, then we had 7 nodes. Then it lasted for a while, and then a little bit after, the, I don't know that color. Okay, the third, I don't know what the name, cyan, maybe it's kind of cyan, right? Okay, cyan is out, and when it is out, this goes back to 6, right? Then there's a moment here in which the purple, right, is gone, and when the purple is gone, then this goes to 5, and then it comes back again, and so it goes back to 6, and then from now on it's always 7, except from a few cases with a few spikes. So you see that the average distance between the transmissions is adjusted depending on the number of robots that we have at each time. And so you see that if we have less robots, we have more tolerance to these delays, right? When they are more compressed, we have less tolerance, which is normal. Exactly what we expected. Now, one important point. You could ask, okay, but how long does it take to reconfigure, right? Because this reconfiguration, and how does it work? Just a little bit on the process. So in order to actually make it work, we use what is called an agreement vector, or it's a vector that actually tells you, or the membership vector, as we tell it. It's just about time to end, right? So I will end right now, and just coming to the end. So so basically we have a vector in which each robot says what is its vision of the team, right? So I say, well, I see robot 1, 2, and 5. I don't see 4 and 7, whatever. And it shares this with all the others. And so they all share this, and by using this, they reach agreement on the current composition of the team very quickly. It takes about 1 to 2 rounds. And then they resynchronize, which means they reconfigure the round. Why is this important? Because, I mean, if I am configured with a round with 3 slots, and that one is configured with a round of 4 slots, it will not work, right? It might work during one round because it's like interference. But then it has to be, sorted out. So it's sorted out quickly. This is just a quick way to tell you important points. So let's see, node 1 is started there, and when it starts, it waits for 1 period to see who is in the network. And then it starts after 1 period, 1 round, it starts announcing itself. When it announces itself, all the others will detect the new robot, and then they will integrate at some point the new robot, and this will, after this, this is called the agreement phase, and the next transmission of the reference will actually be already with a new structure, and all of them will have a different offset so that they are adjusted to the new configuration with a new slot, or with a slot less. So then this is what we call the reconfiguration part. Now, with actual measurements to see how long does this take, right? Because this is without errors. If we have one of these packets lost, then this can be extended for another round, right? And so we can have an extra round on the agreement phase because of packet losses. Or it can be 2 rounds, or it can be 3 rounds. It depends how many packets you miss. So we did an histogram of the lost packets in a particular situation, exactly in the same log that I showed you before in the previous slide with those reconfigurations. And in this case, we had 22% of the actual reconfigurations. They had 0 errors, so it was exactly, in the worst case, 2 + 1 rounds. 65% had 1 extra round, so it took, in the worst case, 4 rounds. And 96%, so plus 10% took 2 extra rounds, which meant 5 rounds. And 4% used 3 rounds. So you see that on average we have like between 0 and 1, and you can say with a round of 100 milliseconds that 96% of the reconfigurations took less than 500 milliseconds, right? So 500 milliseconds, it's pretty cool, right? So you can have the whole structure of your communications being completely reconfigured within 500 milliseconds. Actually, these are worst case bound, so it can be less than that. Right? It depends on the particular situation. All right, so on the use of the protocol, just to finish, it's adequate to disseminate state information, right? Because, we have the current state of the world, and we update the state of the world, and so we share it, we share it, we share it, right? That's cool. Now, if we want to send a stop command or a start command, so an event information, it's not really the thing. Why? Because it would imply, extra delays, right? If we convert the event into state, then it would take at least 1 round of delay in order to have the information propagated. And having 100 milliseconds delay with a stop command, you can see the difference, right? You remember when Kambada was using this conversion, that when there was a stop from the referee box, Kambada was normally moving like half a meter more until they could stop, because there was, at the time, there was a use of the events were converted into state and transmitted inside the RTDB. But they can be transmitted as external traffic, right? And external traffic is still possible. I mean, the other team is using it, so you can also use it. So when you have commands, you can use external, you can send your events, and you can even send your events with retransmission approaches or with explicit acknowledge to make sure that it's a reliable command. So typical behaviors, collaborative ball tracking or formation control, whatever. So collaborative sensing for strategic reasoning, so whatever, so you can use this for any of these purposes. All right. So this was done to support collaboration among autonomous agents through wireless communication, supporting or tolerating interference, errors, multipath fading, attenuation, whatever, and it's a way of sharing information. So it's kind of this middleware. And then we propose this synchronization, this TDMA. It's very interesting that it's, you probably didn't realize, but the nodes synchronize on when they heard the others. So if the others were late, then they also delay. That's what delays the round, right? So they don't use clock synchronization, which is interesting because you don't need to add another service. And clock synchronization, we also compared, and we have measurements that show that this is also better, because with clock synchronization, the structure is rigid, And if you have this periodic interference with those critical patterns, it doesn't move away. It stays there, still sensitive to that. And this one just moves aside. So this is good from that point of view. But of course, it also has some other tricks. And if you ask me, I will, offline, I will be honest, and I will tell you the downside of this part as well. No, it's just, but it's true that the thing is that if it's clock synchronized, you can synchronize everything. You can synchronize all the activities, all the processes in all the robots. And so you can have a state update that is just before the time to transmit. And so this data will be really low age when it is transmitted. And so you can optimize the end-to-end, right? If you have this variable, round, adaptive round, which is nice for some things, not so nice for the others, you don't really do this because there's no common clock. You cannot really synchronize the application level. It's harder, right? So you cannot do that. So you lose something, right? Okay. All right. This is it. Effective RTDB shared memory. So we establish the effectiveness of this. So it creates this separation of computation and communications, and it provides data age information, which I think is interesting. We are doing now is adding admission control and admission control based on actual localization to use this on vehicular networks. That's what we are trying to do now. So some acknowledgements first to Federico, because this is the guy that actually built what you saw here. It was his PhD work. This was done essentially inside the Cambada team. It uses infrastructured communication. I also have to state my deep appreciation to the other student I have now, who is actually finishing his PhD now, but did a complete ad hoc version, which has completely different problems in terms of synchronization, because synchronization has to be propagated, and enforcing consensus in a distributed mesh is much more complicated. And he also did this point-to-point in a mesh with routing and relative RF-based communication. And my last acknowledgement, of course, to the Cambada team, to the whole Cambada team that allowed most of this work to be done, and many collaborations that actually allowed Frederic to do his work. So thank you very much. I would be more than pleased to answer any question that you have or any doubt. If I can answer, I would be more than happy to do it. Thank you. Long time, no? Yeah. Too long. A little bit.
We have a dinner.
Ah, right.
Anyway, any questions you'd like to address? Yeah.
Why do you use UDP and not TCP?
Well, the thing is, we do multicast. And so TCP does not allow multicast. It allows only one-to-one. The other reason is that TCP has all this interference with the timeliness control, because it has this acknowledgement, the windows and stuff, and so you cannot really control timing with TCP, right? It's a little bit strange. But essentially, you cannot do broadcast. What you could do is one-to-one. And we also did a paper in which we compared. Maybe if we do one-to-one, right, in all of them, it's better. So because when you do, this is the other downside of the work, when you do broadcast, typically the speed of transmission is lower. So your packets take longer, and so you use more bandwidth, right? It depends, because you can compensate. You can actually, make it so that your device driver actually uses a higher speed anyway. But the thing is that it turns out that when you send one by one, it's more complicated for your protocol. It's also more overhead that you impose on the system, and actually it's basically, if everything is okay, it's fine. If you start having errors, then it adds a lot of overhead because of the retransmissions of TCP.
Right. You said that like humans, they are supposed to talk one on at each time.
Yeah.
Sometimes humans interrupt the other human. Is there any way on the protocol that we can, for example, imagine you are transmitting a kind of piece of information, and your information is more relevant at that point, well, to a point that you should interrupt something and transmit you and the other way.
Well, thank you, Fernando, because that's a very good question. The thing is, one of the targets of our protocol was exactly to support that, because when you allow each robot to transmit, you know, on its slot with a lot of separation in between, you can allow a lot of traffic to go in between. So the interference that you cause to that particular case is relatively small. It can be one packet or two packets, depends on how much you transmit every slot, right? So if you slot, or I mean, when you come to this time of the day, it's very hard to make sense. But so if you transmit only a short information, like only one packet with an update of the RTDB, then this is the maximum interference that you can cause to another transmission of higher priority. Because maybe this transmission was going to go now, and you just started doing a transmission of the other. So you have to wait until the end, and then you go. Right? So it's much better than other cases in which you transmit you know, large size of information, large chunks in a burst, and then this interference can be the whole burst. Right? So we don't have that problem for the moment.
A couple of questions, if we have time. Regarding the age information for shared items, because of the problem that we have to wait if there's an interference with another transmission, and we don't control that, we can't change the age right before transmitting again. Is there any hack that we can do on the driver or kernel or something that we can also encompass that information of that extra age time that we didn't include before?
Yeah, there are several parts that maybe they are outside. So that picture with the age, right? So if we go there, yeah. So if okay, all right. So if you see this, when you have interference in the traffic that creates delay in the traffic, then it appears here. We don't know it, right? So I think this is one of the questions that you're asking, right? So we don't know it, and to measure it, it's a little bit tricky, because the thing is, it's already, when you send it to the device driver, you kind of lose your control of it, right? You hand over to the device driver. I think that, I don't know, but maybe looking at some device drivers that could exploit this feature of this transmit interrupt that tell you exactly when a packet went out. But we never did it. So, but maybe that way, but this means programming at the device driver level, right? So you need to know the device driver and see if the device driver gives you that functionality and allows you to enable it. Changing the device driver, I don't know, maybe a possibility, but these are, you know, complicated device drivers, so I don't know. But we never did that. So what we do here is that we did those, histograms with the delays, and so we get, an idea about what we should use here, right? Now, if the environment at runtime is pretty much different from what you plotted, then this will be different. An interesting thing would be to online, you do this histogram, right? You measure, you have an idea about the delays. It's not easy to measure because you cannot measure it from your side. So you need information from the others. But the others can tell you how late you were with respect to the expected transmission, right? And so if you share information about the delays, then you can build a distribution and you can online adjust this parameter, right? Now, there is something else. On the producer side, we can have something before this, right? Because when you are generating the data, then before you actually do a put, there may be some time in there. You may even have a preemption of the process. Some other process starts doing something else. And so the time from the actual capture of the data until you actually write it there can be, now this can be sorted out by using this kind of non-preemptive function. So by disabling any kind of preemption between the actual sampling and put inside the RTDB. So that part we can improve. And the same thing here in the consumer, right? Once you actually extract the data. So these are the things that I can tell you.
Another question based on your expertise. Another solution for that would be to synchronize clocks and to transmit global timestamps.
Yeah.
Do you believe that protocols like NTP and similar ones are usable in the conditions of a game? Or would you synchronize before a game and then just hope?
NTP itself is relatively poor, right, for this environment. It's too dynamic. And it basically uses NTP. It uses these round-trip delay measurements that it does from time to time, and then it has the the good clock, the master clock, let's say, kind of, or the upper layer clock that is used as a reference, and then it basically synchronized to that. Now, you could use other protocols. Precision time would probably be better, but it has more, let's say, the way that it works, it has, let's say, more overhead, maybe, in some sense. But it's much cooler, and it's much more precise. Now, other thing is that there are other protocols that are, there's a framework that we've used several times, which is very cool. It's called Crony. And it really gives you a good synchronization. You don't really care about anything. You just install it, and it corrects your clock, right? And then you can use your clock as a global clock. Now, you should be aware that this has a precision anyway that is limited. In stochastic terms, you can actually achieve a relatively, sub-millisecond precision depending on the, the load of your system. But in fact, it will always be on the milliseconds range, the precision, because it depends. If you have a high load with high variability of delays, then there's no miracle. I mean, you cannot really compensate for these delays that are completely, let's say, unexpected, or you don't know exactly what you are going to get, and so you cannot really compensate for it in the protocols. Now, I think clock synchronization is really cool. I mean, because you can do a lot, right? Because you can synchronize in time all the robots, all the activities. The problem in our particular case, and that's what we are also compared and checked, is that if you use clock synchronization to generate this TDMA, what you do is that the round is rigid, and the slots, when you create them, they don't adjust. I mean, you use the slots based on this offset with respect to this time. And this does not allow you to get rid of these critical interference patterns with periodic interference. But maybe there is a way that you can shift from it. Using clock, so maybe something can be done there. I'm not really 100% sure that it's better not using than using. It's something that is open, right? What is true is that you need to install it. For example, using Crony, you also need to know that Crony is a centralized clock synchronization algorithm, which means that if the master crashes, then all the robots will diverge. But of course, they diverge slowly, right? But still, depending on the length of the game, and I don't know. But for the precisions that we typically use here, it should be okay for a game. It's the same thing with, for example, the ROS, for example, the ROS topics, which all the connections are done by this master, right? So the master dies. I mean, if a robot dies and comes back again, then it cannot connect with the rest. So it's gone. So it's these things. That's why we did something that is completely, separated from all that, and it's completely distributed. And that was the target. And so no need for clock synchronization. Is self-sufficient, and so that was the purpose. Yeah. That you can do that. It's what is typically done is this fault-tolerant average, in which you get information of all the nodes, and then you see how far the clocks are. You just get rid of the farthest clocks from the average, and then you average the others, and you use it as your reference clock. In this case that we are sharing this agreement, we can also share the clocks, and we can actually build a matrix, and we call it a vector, or let's say a clock matrix, because we can share the vision that everybody has about the clock of the others, right? And then we have on each line, I have a robot I, and I have the clock of all the robots that robot I received. And then everybody has this image. Of course, it's kind of different, but then they can get rid of the clocks that are bad, and then they can do average of good ones. But then you have to do that, right? So it's extra burden, so we don't do that. But you can do that, of course.
Other questions? Yeah, during dinner, lots of time. My question is that we are now 50 minutes away from the schedule for dinner. lots of times.
To me, it's my usual lateness.
Yeah, I know. But I don't know if someone still wants to go to the hotel, or if you like to go directly to restaurant. Yes, you can, no problem. Okay, so.
Can I ask you something? Just a quick question is, if those of you that have had experience with RTDB, it's we never asked for it, but having feedback would be nice. I mean, because I mean, this Federico finished his PhD, is busy because in his school, they give him a hard time with teaching, but still he would be, interested in maybe maintaining, collaborating, and doing. We do some updates from time to time, but just to say that if you see something that could be, improved, updated, it would be nice. Just. Yeah. All right. Then you let me know your feedback. You can say honestly, this is crap, man. I'm not going to use it. So, yeah.
I don't know. There is still,
yeah.
I don't know how many teams, but there is already some teams using RTDB at this point. With some, maybe they have also introducing some changes from their own changes, and of course,
yeah. So that would be nice
feedback
to
would
share.
be nice.
That would be nice to share.
Right.
Yeah.
Month ago. Yeah, that's a question. How is going? How is VDL going? Okay. So, question, as I said, is that we have a restaurant scheduled for 8 o'clock. Not Central European time, luckily. And so, I don't know if some of you would like to still pass through the hotel, or if you'd like to. Are all the teams have cars? It's not necessary actually, because are very small, so we can walk directly to the restaurant and then come back, or wherever you have your cars. We have one robot. Yes, you can.